All right. So I want to welcome everyone to this month's meeting of the Houston Functional Programming User Group. We are very excited to welcome back Richard Feldman. He is, at this point, an old friend of the group. He's spoken with us a number of times now, and it's always a ton of fun and super, super interesting. And so today he is here to speak about all of the latest developments of his language, Rock. So I will turn it over to you, Richard. Take it
Awesome.
away.
All right. Thanks so much. Let me double check. Can everybody see my screen okay? All right. Great. Yeah, so this is going to be sort of a two-parter. So part one, I'm going to sort of talk through some high-level concepts with slides and stuff. And then basically in part two, I'm going to switch over and open up a code editor and just have basically some code snippets that we're going to talk through. Feel free to interrupt me at any point and ask questions if you want. I mean, this is a meetup. It's not like a conference talk, and there's not that many of us, so it's not like it's going to be, a big deal if you want to stop me and ask for clarification or just have a little discussion of something. So we can kind of keep it nice and lightweight and chill while I talk about some new ways to rock. Okay. So, this is the Rock programming language we're talking about here. Rocklang.org is the website. If you go to the website right now, you're going to see everything that has been built over the past couple of years. We had a Rust-based compiler. We had a design that's in many ways similar, but in many ways also different from the design I'm about to talk about today. We're in the process of rewriting the compiler, largely in order to support all these changes, and we've decided to use Zig as the language for the new compiler. If you try to use that compiler right now, you won't be able to do a whole lot with it, but we're getting very close to making it usable enough, at least, so that hopefully people will be able to do advent of code in it this year. Um, so the tagline is it's a fast, friendly, functional language. So fast both in terms of runtime performance as well as in terms of compile time performance. We generally want to compete with Go when it comes to runtime performance. Like ideally, we want to be faster than Go, but not as fast as memory unsafe languages like C or Zig or Rust supports memory unsafety. So I'm going to put it in that category too, even though, of course, Rust likes to be memory safe. Friendly in terms of user friendliness and also friendly community. User friendliness being things like really nice error messages. Rock is a direct descendant of Elm, and we're going to talk about that a little bit later. So having really user friendly error messages is a really important thing to us. Also friendly in terms of like having nice, simple APIs, not a lot of ceremony, not a lot of complexity in the types. And of course, functional because it is a functional programming language. It's not multi-paradigm. It's not like hybrid OOFP. It's just a functional language. Um, so one of the sort of defining characteristics of it, like within the category of functional languages, is that as a language, it has no concept of mutable values. As a behind the scenes compiler optimization, it is actually allowed to perform mutation at runtime, but only when that would be unobservable. So an example of this would be if you can imagine if you have a record of values and you're like, okay, I want to take this record and I want to make a new record that has almost the same values in it, except I'm going to change just one of them. Well, if you use the first record again later on, then of course the distinction will matter whether you mutated it in place or not. If you did mutate it in place and you're looking at the first record later, that's observable. But if the compiler can detect that you never, ever, ever look at that first one ever again, anywhere in the program, there's just no code path that does that, well, the optimizer can just be like, we'll just go ahead and update that in place, and literally no one will be able to tell your program's just going to run faster. So as a concept, we don't have mutable values in the language, but as an optimization, we do have that sort of opportunistic mutation. Effects are represented in types. So this is something that, for example, Haskell and Elm do. We do it differently than how they do it. We do it kind of closer to the world of algebraic effects. Technically, what I think we're doing could be considered binary algebraic effects, but it's a lot less fancy than the algebraic effects systems that you'll find in like OCaml or Unison or Coca. This is a very, very simple concept to the point where calling it algebraic effects honestly feels a little bit like I'm overselling it because it's so simple. Okay, so here is the logo for the Gleam programming language. And in Gleam, you have a function called append, and it takes two lists. So this is Gleam syntax for like the signature for this append function. So it's like, give me a list, give me another list, and I will return a third list. So A and B are just the names of the arguments, and then the types of all three of these are list A, list A, list A. This is a pretty mainstream syntax for this function signature, and it's a pretty typical functional programming concept. You're like, I have this list, I want to append another list onto it, and it's going to return the new one. All three of these are immutable lists. Here it is in OCaml. So syntax is a little bit different. So OCaml uses white space for application rather than like parentheses. So like in Gleam, you have the parentheses here after the list. This is a pretty common concept for like function calling in most languages, syntactically speaking. It's kind of unusual for Gleam to do it at the type level. Usually you'd have angle brackets here in most mainstream languages, but the parentheses is pretty straightforward. You can imagine they're like the angle brackets, but not as sharp perhaps. Um, and the other difference, of course, is that the OCaml version is curried. So you see the two arrows here. So if you were to call append in OCaml passing just one of the lists, that would be allowed, and it would return a new function that just takes the second list and then appends that to the first one and then returns the final list. Whereas in Gleam, if you call it passing only one of these, you'll just get an error that says like this function takes two arguments. You only gave me one. You need to give me another one. There are pros and cons to both of these things. So, in the ML family of languages, such as OCaml, so this is like descendants of the originally called Metal language by Robin Milner. OCaml, that's what the ML at the end of OCaml comes for, is it's a descendant of ML. Well, it's a descendant of Camel. OCaml was like to add objects to to Camel, but the objects, as I understand it, are not that actually that popular in the OCaml community. But in the 90s, everybody was adding objects to everything, so it's understandable. Um, and then you have like Haskell and Elm, which also are curried languages. One of the trade-offs of currying is that if you call a function and you forget to add an argument, like you just leave one off by mistake, in Gleam, you will get a very nice, helpful error message that says, you forgot an argument. In OCaml, Haskell, Elm, etc., all the curried languages, you get a much less nice compiler error for that because it's just allowed to leave off an argument. And so what you'll get is something where it's like, I think you're using this as like this blah, 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 super long function name, but I'm seeing blah, 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 with like one other argument. So, what's the deal there? The error is not like as helpful as it could be, and it's not right in the place where you would expect it, because right in the place where you made the mistake, you did something that the language allows and silently will propagate because it's an intentional feature, and then you see it later. So these are some differences between these two. Here's one more signature of append. So this is the Elm version of append. Elms looks kind of like it has elements of both of these. So you have like list coming before the type parameter. Elm is of course curried like OCaml. It doesn't have the parentheses like Gleam does, and it doesn't name the arguments like Gleam does, but they're in the same order as opposed to like OCaml, which puts the type variable first. So again, like a little bit of a different syntactic style here. One thing that I would note about the Elm signature is that it is saying something that these are not. So in Elm, what this arrow means is pure function. Now in Elm, all functions are pure, so this is like not that interesting of a claim. It's not like Elm has a separate syntax for impure functions. Um, but it does mean that when I look at this signature in Elm, I'm learning more about this append function than I am in OCaml or in Gleam. In Elm, when I call this function, I know for sure that no side effects are occurring. And I also know that for sure, if I take these things in, it's going to give me this. If I take the same two lists in as arguments, it is for sure going to give me the same list out every single time. There's no concept in Elm of like, oh, go read from a global mutable variable or a database or do a network request, and then like also add that into the mix of how I'm deciding how to return this. OCaml and Gleam both allow side effects, so these function signatures, although they look similar, it's not just a syntactic difference between these. The Elm one is actually saying more than these other ones are saying. Now in Rock, we have again like a slightly different syntax from all of these. So we have now in in the new version of the compiler, the syntax is kind of like a cross between Gleam and Elm, I would say. So it looks very similar to Elm, except Rock has never been a curried language, so we don't have the arrow here. But we have adopted the Gleam syntax for reasons that will become apparent later for the type parameters, so like the parentheses. Much like the Elm version, the Rock version is saying that stronger thing. Like it's saying this is a pure function. When you call this function with the same arguments, it's guaranteed to give you the same result, and it cannot do any side effects. Okay. Now, oh yeah, I forgot to mention, in these languages, they call it append, and in Rock, we call it concat. The reason we call it concat is because we have a function that doesn't actually make sense in these languages, but does make sense in Rock. That is this function. So we call this one append. So this one's give me a list and give me one element, not a whole other list, and return a list. Now, the reason this function makes sense in Rock, but not these other languages, is that in Elm, OCaml, and Gleam, list refers to a linked list. So appending one element onto the end of a linked list is comically expensive. You really, really don't want to do that. It's a very, very highly discouraged. So it kind of makes sense to just be like, yeah, just like use that name for something else because we don't really want people to be trying to do that. You have to traverse the entire list and like it's just a disaster, um, especially in like an immutable linked list like this. Actually, I guess with a mutable one, it's not necessarily any better. Anyway, point being, prepending to linked lists very cheap. Appending to them definitely not cheap. But in Rock, we just have append and prepend. And the reason we have that is because these are using the term list in more of the sort of Python Java sense, which is to mean just like a flat sequence of elements. Um, Basically, what happens in Rock when you do this is we do that sort of opportunistic mutation thing. If you have extra, this is basically a flat array in memory that can sort of grow automatically. So this would be like in Python, it would literally be called list. In C++ or Rust, it would be called vec or vector, um, something like that. And Zig would be array list. And the basic idea is just like this operation, especially if you have excess capacity, is extremely cheap. And doubly especially if you have a unique list. In other words, like it's not being used later on. Um, this will just be as fast as it is in C++ or Rust in Rock to do this operation. So very, very cheap, but it's because it's a different data structure. Different trade-offs. Okay. So
Can
we've
I
changed
can
the,
I interrupt real quickly?
please. Yeah, go for it.
I'm curious as to why you decided not to support currying. Just because I find currying so partial application to be so helpful and
Yes.
useful.
So we have an FAQ entry on that. There's a couple of different reasons. Without going down a big rabbit hole, I would say there's a combination of factors. So one is the error message quality thing I mentioned earlier. Like I agree. I mean, I have used currying. Obviously, I am a huge fan of Elm. I've used it plenty of times. Um, uh, the type mismatches that you get, especially if you have like three or four arguments in your function and you accidentally forget one of them, they're one of the few cases where I would get type errors that are not nice in Elm. Is when I like forgot something and then because of currying it was allowed and then somewhere down the line, like slightly later, it caused a problem. Uh, Another is that because I spent a ton of time teaching Elm to beginners, like I logged like more than 100 hours of like in-person time with different workshops, just teaching beginners Elm. There were two things that beginners always get stuck on. Like Elm's a very user-friendly language and very beginner-friendly language in many ways, but the two things that I always saw people get stuck on very, very commonly, like half the class or more, one was decoders, and we'll talk about those a little bit later, how Rock does those. And the second one was currying. It would just be like some people would get it, but then a lot of people would like I would just walk through the whole explanation of like here's what's going on. It's a very simple concept. Here's like look, let me show you like applying these things one at a time. So oh look, it all works out. Here's why the type signature makes sense. And of course you have to explain it because as soon as the beginner sees a function like this, they're just like, why are there two arrows in it? And you can either be like, don't worry about it. It's just two arguments. Just yeah. But then of course as soon as I get the type mismatch, they're like, I don't know what I'm looking at. This is crazy. Um, so you have to explain it, and a lot of people don't get it. So I think there's a pretty significant
Yeah.
beginner friendliness, and also for expert users, a nice error message thing. The third thing is that, and this is where it gets into a rabbit hole, so I'll just try to be brief about it. But uh, I have concluded after spending a lot of time trying to see the light and get the benefits out of it that point-free function composition is a trap. It feels really cool and it's these like neat puzzles. But ultimately, it's just makes your code harder to read, and it means that anyone who comes along and reads it later is going to spend a lot of time mentally translating it into the straightforward way of writing it, and it's just something you shouldn't do. Currying makes it easier, like facilitates programming in a point-free function composition style. And I
Mhm.
think that's actually a point against currying, is that it's sort of like it's a pitfall, not a pit of success. And I think if you don't have it in the language, it just like naturally draws you to not even waste time with the shiny puzzle of trying to do things in a more point-free style because it's just like harder if you don't have currying. And I think that's a selling point of not having currying.
So
Um,
just to sorry,
yeah.
just to clarify though, so functions are they're first class objects in the language?
Yes.
So you could return a function. Like I'm
Oh,
not
sure.
saying that, but like one way that I use partial application is like factory functions or something like that. But that seems like that would be totally fine in
Oh
this
yeah, of
case.
course. Yeah. So you can always like opt into it.
Yeah, yeah.
Like the difference between like Rock and Elm is that if you wanted to write it in a curried style, we actually syntactically require you to put parentheses around this. That's really just a clarity thing. Like I
Yeah, that's
could have
fine.
just
Yeah.
made, yeah. Um, Functions are so first class in Rock that actually literally we only have lambda syntax. Like there is no other syntax for defining functions because I really want to like hammer that home that like these are not special. It's just like there's no special like define a number syntax. It's like no, you just say x equals 5, right? It's like yeah, if you want to define a function, you say my function equals lambda. Like that's it. That's the one syntax for defining functions because I really want to emphasize like they're just plain old values like anything else. You can pass them around, do whatever you want with them. Put them in lists, take them out of lists. You know. Um, yeah, but I think although it's conceptually very important that it's like functions are plain and ordinary and there's no special type of functions, they're all just like they're all just functions. Um, there's no like, distinction between like top level functions versus lambdas, for example. Having said that, it is still, I think, important to, lead people down a path of success because when you have functions as like the thing that you're using all over the place, I do think it's very, very easy, and in fact, the default to go overboard with point-free function composition. Um, and yeah, I want to create more of a pit of success around that. Having said that, I think currying is fine. Like it's like I don't think languages that do currying are bad. I love Elm. Elm does currying, like it's fine. But I also think that like not currying is fine. And a super common beginner rock experience, it's like to the point where it's not quite a meme, but it's like the people who've been around the community for a long time just watch this happen over and over. Is someone comes into Rock Zulip and they're like, I really like this language. I don't understand why you took out currying. I'm obviously really gonna miss that. And we'll be like, just give it a try. And then like a couple months later, they're like, I thought I was gonna miss currying, but I don't. It's weird. And I'm like, yep, yeah, we just watched the cycle happen over and over. It's like you think you're gonna miss it, and then you don't. So, anyway, yeah. Any other thoughts, questions about currying? Okay, cool. Um, all right, so this append function doesn't make sense in those languages because they use linked lists. Because we use a different data structure for lists and we have the opportunistic mutation thing going on, this makes sense in Rock. Now, in Go, you also have a function like this, but it works differently. So Go calls it append, and the type is a little bit different. So you're saying like, give me a slice. It's like a little bit more of a convoluted function, but it's the same basic idea. It's like you can stick one thing on the end, or I think this means you can like put more. It's like sort of var args. Like you can be like, give it one or two or three or whatever. Point is like if you did want to stick one thing on the end, this is how you do it in Go. Now, this is quite different because here, this arrow, meaning this is a pure function, tells you something that, again, the Go one does not, which is that the Go one is mutating this in place. You call it passing this first argument, and it's like, it's potentially mutating in place. Sorry, I should say. I think this one actually returns it in Go, but the Rust one does not. Right. So the Rust one says, I take a mutable reference to the first one, which is Rust marking like, it's like, okay, it's not a pure function, but I'm telling you that I'm mutating it. And you do know that the second one is not, well, okay, that's owned in Rust, so that's a little bit of a rabbit hole too. Um, but Swift also has this like mutating func. So like mutating being this keyword that sort of tells you like, yeah, I'm actually going to be doing the like mutating it in place thing. So the Go one's not, but you don't actually know that for sure because Go doesn't have a distinction of like that like ampersand mut that Rust does or the mutating that Swift does. And this is common in a lot of languages where it's like, yeah, this thing could be mutated. I don't really know. And of course, none of these say anything about side effects. But like of these languages, Rock is the only functional one, so it kind of makes sense that Rock would be the one that's like, I guarantee no side effects. Whereas like the Go one, even though it doesn't do side effects like the Rust and Swift ones do, it doesn't really tell you that in the signature. There's no like hint that that might or might not be happening. Um, Now, there's also the topic of side effects. So here is a glean function that very, very much does a side effect. This is read line from a file. So this returns a result of either string or nil. So for those who are not familiar with result, this is basically there's a lot of names for this: algebraic data type, tagged union. This is a form of sum type. There are other forms of sum types, but this is one. Um, but basically, the idea, sorry, Rust calls it an enum. F sharp calls it discriminated union, I believe. Um, the basic idea is it's just like I either have like an okay or I have an error, And if I have an OK, it's going to be a string associated with that. So if I'm in the OK scenario, if this thing returns an OK, then I can sort of say, okay, what is the string that's associated with that OK? And if it's an error, then I just have this thing called nil, which basically means there's no additional information there. So the point is that what I get out of reading this function from Gleam is I know that this is a function that takes 0 arguments. Um, I believe sorry, it's reading from standard in. That's right. And then it's giving me back either I got a string from standard in or I got nothing, like it errored out somehow. So something went wrong with reading from standard in. Here it is in OCaml. Again, slight syntactic difference. Like Gleam has a first-class concept of 0 argument functions, whereas OCaml, like many languages in the ML family, doesn't have a concept of 0 argument functions. So you do need to take some sort of special, like they call it unit, but like in Elm, this would be empty tuple. It's basically just like some sort of type. You have to give it an argument, but that argument has no information in it. And then it just gives back a string. So the OCaml one chooses not to do any error handling. It doesn't have a result equivalent. It doesn't say like, oh, what if it's like a broken pipe or something like that? They're not handling that. Or maybe it throws an exception or something like that. I don't actually know. In Haskell, you actually do model that this is something that does an effect. So in the OCaml and Gleam ones, there's no hint here that this is a side effecting function other than sort of like the name and like maybe you can kind of infer that from like how it looks. But it doesn't formally come out and say this function does a side effect. Haskell, like Elm and like Rock, is a language that has a first class distinction between effects and not effects. You can tell it just by looking at the type of the function. Now, in Haskell, as with an Elm, you have that distinction by basically saying all functions are pure. And so the way that you know that there is some effect going on is that it's represented in the return type of the function, or in this case, this actually isn't even a function at all, which is another way you can represent this, like rather than having unit or a 0 arg function, is basically just like, yeah, this is an IO. And then the concept of an IO is basically a value that describes some sort of operation that you're going to perform that has some sort of effect. And rather than being able to take this value and sort of execute it anywhere in your program, unless you use unsafe perform IO, but we'll just pretend that doesn't exist for the purposes of this talk. The point is that the way that you're intended to use this is that your sort of main function equivalent has the type IO, and then all of the other things that you call in your program that you want to do any IO, those functions all need to return IO, and all of that gets sort of composed together and handed off to main, and main says, great, I've got this gigantic value that describes all the IO that I want to do in my program. I'm going to sort of traverse it and interpret it and perform the effects and then pass them along. And Haskell has special syntax sugar to facilitate this, which is called do notation. I mean, it's used for other things, but primarily in practice for I/O. This is the type in Rock. So the way that we do this, and I talked about this at the last time I was talking with Houston Functional Programming. Back then it was a plan, and now it really exists, both in the Rust compiler and also in the new Zig-based compiler. This is basically we have two types of arrows. One is the pure function arrow, which is the thin arrow, and then we also have thick arrow, which is this is an effectual function. This is basically conveying the same information as the Haskell one, where it's like, yeah, this function does a side effect. If you read the line, it's so this is our syntax for a 0 argument function. It's going to do some sort of side effect, in this case, reading from standard in. And we do have the same thing going on as Gleam, where we say like, hey, there could be some sort of error that happens here. Like I might be able to give you a string, but maybe I can't because it could be broken pipe or something like that. And the way that we do that is we model it with a data structure that's exactly the same thing as result, except we are giving it a try to name it try instead. Basically because it's more concise, and also there's this really annoying thing that happens when it's called result, even though there's a lot of languages that call it that, which is that I want to name something, like I want to name a variable, like the outcome of the function I just called, and the word for that obviously I want to choose is result. I want to say result equals and then call this function, and then like use the results of calling the function later. The problem is if you have this in your standard library and it means like operation that could fail, then naming a variable result is really confusing because on the one hand, it's the obvious name to choose for the result of a function you just called. But on the other hand, it like suggests that it's going to have the type result, but it actually doesn't. So that just kind of gets confusing. So we're giving it a shot to call it a try. So try in the noun sense, like this is like give it a try. Um, So yeah, so this function, you can read this as sort of saying like, when you call read line, I'm going to return giving it a try. And if that try succeeds, then it'll give you a string, and otherwise it'll give you a standard in error.
So there's nothing like IO specific about try, right? It's just like
Oh,
you
right.
could
Yeah,
have a pure function or like a
totally.
non-side effectful function return try. Okay. And
Yeah.
then in this case, is the exclamation point, is that like a recommended thing, or is it something like an exclamation point at the end of the function turns it into a side effectful function or
So it's just the arrow that, from a types perspective, turns it into a side effecting function. However, we do have a very, very strong convention to the point where the compiler will tell you should add an exclamation point.
okay,
Um,
good. Yeah.
and the purpose of that is that when you're calling the function in the middle of your, code, uh, there's no other way that you could tell, like, where are the side effects happening. So we like having that as a really strong compiler enforced convention. I mean, it's a warning, but
Yeah. No, it's good.
basically
I
so
think it's
that like,
smart.
yeah,
It's
if you have a giant function and it's like there's only one exclamation point, and it's like, oh, the rest of this is all pure functions, cool. But like that there, right there, that's where the effect is happening. Um, yeah. It also has a nice thing in the standard library, like when you have higher order functions. So languages with algebraic effects can do effect polymorphism. We talked about it and we decided that it was going to be simpler to do it this way, where it's just like sometimes you have a higher order function where you want to be like map is a bad example, but it's always the first one that comes to mind when I think higher order functions. You have like map and map bang, and the only difference is that like one takes a pure function, one takes an effectful function. Um, in the standard library, this comes up a decent amount, but outside of the standard library, so far it seems like it comes up very rarely. But it's actually a really convenient way to like sort of namespace those two. So it kind of serves a dual purpose of like helping you out in the code and then also making it so that it's like really, really blindingly obvious how you get the effectful version of a function in the cases where it's like higher order and it kind of makes sense to have one of each. Anyway, yeah, so the main takeaway here is just that it's common in a lot of languages to just not have the type reflect at all whether or not there are side effects happening. The way that Haskell does it is by changing the value of the return type, and the way that Rock does it is by just having two different flavors of function. You just have a concept of pure functions, you have a concept of effectual functions, and Rock doesn't need a do notation or anything like that because it's like you still call the function in the normal way. It's just that if it has an effect, then it's going to do an effect.
so
As you
are
might
there
imagine.
I
Oh,
was
go
just
ahead.
going to ask, are there different like so this is like an IO effect, right? Like so this is sort of like something where you open something with the operating system
Yeah.
and it gives you a line of but then is there are all like are other kinds of effects like kind of like do you have a concept of like an asynchronous effect or something like that, or is that
Uh,
handled in the same way, or is it no I'm
no. So asynchronous
curious.
effects. How do I put this? The short answer is that we're kind of doing what Go does. So
Yep.
Go does not have a concept of async await,
Sure.
but Go has kind of the performance characteristics of it anyway, because in Go, all I/O is defined to be potentially non-blocking behind the
Yes.
scenes. We're doing the same thing basically.
Okay.
We're
Like
taking the
a
same approach as
yeah,
Go.
it's like a red green
Um,
thread or something like is I might be using the terminology wrong. I don't know this stuff as
yeah,
well,
yeah.
but
I mean,
uh,
that's an implementation detail of how Go
okay,
does it in
okay, sure, sure,
particular.
sure.
You don't have to do it that way. You could just compile to like silent async await, like what do you call
But
it?
there's
Stackless
other
versus
kinds of
stackable
like
code.
effectful stuff, right? So there's reading files,
Yep,
but all kinds of anything that like might have like a side effect, either reading from an outside source or
yep.
even something like inside the code would be
Random numbers,
yeah,
like
yeah, exactly. Time,
yeah. If
like
you are
that kind
right,
of stuff.
which is based on
Okay.
system time usually. Yeah.
Yeah.
So right. So all of that. So this is why I mentioned very briefly earlier the term like binary algebraic effects. If you have a full algebraic effects system like OCaml or Coca or Unison, um, you can get granular about it. So you can have like
Yeah.
a function type that says like this function potentially does like network I/O and database access, but not,
Yeah.
standard in, etc. Um, we intentionally decided not to do that.
I, yeah, I
Part of
think
the
it's
reason for
smart.
that is it's like
Yeah.
it's so simple. It's just
Yeah.
like side effects are pure. That's it. That's the distinction. To me, that's the higher order bit. Like when I'm doing like fu- functional programming in a language like Elm or Haskell, where you have like an actual separation at the type level between pure functions and not, that's like 95% of the benefit to me. Probably more than that, honestly, is like, is it pure or not? That's what I want to know. So we're really leaning into that. And one of the nice benefits of this is that the types get a lot simpler because we experimented with very briefly. This is like kind of digging up some history here, but with basically having a system where, to make a long story short, you could see in the type all of the effects it was doing, and it just didn't feel nice in practice. It felt like it was a lot of like the amount of ceremony that it took to sort of keep up with that. And like as soon as you want to add a new like, oh, now this thing needs to do a network request, but it's cached. So now we need to add files to like all these different things. It just didn't feel like it was like pulling its weight. It was just making the types a lot longer, and we weren't really seeing a corresponding benefit. Not that there was no benefit, but it's like the cost outweighed the benefit. So that's where we ended up at this. Is just like this feels like it's really, really lightweight. It's very easy. You don't need special syntax for calling them. You just call them normally. We do purity inference, of course. So like if you try to call an effectual function from within a pure function, it's like, no, don't do that. Um, the compiler will tell you about it. And of course, the compiler can, without you having to annotate anything, infer like the purity or not of everything because it knows all of the like baseline set of effectual functions, and all other effectual functions have to be built off of those. So the compiler just knows at all times with complete accuracy which functions are pure and which ones are effectful, and it can enforce that accordingly. We actually do in the new compiler make use of this semantically. So one of the things that we do now is we have compile time evaluation of pure functions. So if you do like a constant, if you see like foo equals anywhere in your code base, really, and foo is like nothing inside of foo is like depending on function arguments, right? So like at the top level, or if it is inside a function, it doesn't use any of the function's arguments. Um, we just evaluate all of that at compile time now, which means you can do some kind of cool things that maybe otherwise would require like a separate build step or something like that. You can just like call the functions normally, and as long as they're all pure, you're all set. If you combine that with the fact that Rock also has a language feature where you can import arbitrary like text files or even just binary files from disk, and just bring them into scope as values. What that means is you can do a lot of like pre-processing type stuff that again you might otherwise need like a build extension or something, just using completely plain ordinary Rock code. And we're just like, yeah, we'll just evaluate all that compile time. We know it's all pure functions, so we can just cache it all too. Like we know that there's no need to like invalidate the cache and potentially rerun it because like I don't know what if it needs. It's like no, they're pure functions. Like they're perfectly cacheable, and also they're perfectly deterministic. So we know that they'll like work the same way on everybody's machine, like given the same inputs. So yeah, so we're not just doing that for the sake of the sort of like code organization benefit and the like understanding of what the implications are of calling functions and debugability and all that. We're doing it for more than just that, and that's something I think is yeah
Quick
underexplored
question
in the world of
on
languages. Yeah.
the evaluating pure functions at compile time. Do you have restrictions to prevent like a indeterminately long compile time or like solving the Turing problem type compiler?
Uh, so we don't, and the plan is that we will allow you to run absolutely anything at compile time if you want. The plan is to avoid situations like that. There's a lot of tricks we can do to make it so that you can easily diagnose when that's what's happening. So, for example, we can do things like we run all these on a thread. There's a separate like sort of monitor thread that's like, okay, this one's taking a long time, and we can just tell you like, hey, here's a like stack trace of like what's going on, and this is what you're waiting for. Maybe something's stuck in an infinite loop. Who am I to judge? Maybe you just are doing something really expensive at compile time, or maybe you're running on a super slow machine, or a virtual server that's like got a 1/16th of a core to work with. Maybe that's why it's taking so long. But FYI, here's what's taking so long. Maybe you want to stop it, and and so forth. Um, if that doesn't prove sufficient in practice, which I kind of think it will, but you never know. Uh, that plus like people putting timeouts on their build servers, whatever. If that's still not, if somehow it is still a problem in practice, that of course you can't like the halting problem is real. um, then there is another trick that we can do, which is like super fancy, and I assume not worth it, but maybe it is, which is you can't solve the halting problem, but if you are specifically in a pure function, there is a point where you can say, okay, I can statically determine like where potential cycles can occur in the code. So you have like this thing can recurse in this way and this way and this way. And based on those cycles, you can say, all right, well, here are all the inputs to that cycle. Like this function argument, this function argument, this. At that point, if you get the same set of function arguments, multiple times, you're in a loop. So you can create that state at runtime. This is not statically doable, but it is doable at runtime. Like maybe you get through like 10,000 iterations of a loop and we kind of like switch into this mode and we're basically like, okay, take a snapshot of like the cycles that we know exist, um, write down all the variables we've seen. Every time we go through another iteration of the loop, update that entire state. And if we ever see a duplicate state, like we come back through again and we see a set of variables that we've seen before, we are definitely in a loop because this is a pure function. So nothing is going to break us out. It's like you get the same set of inputs, you're going to get the same set of outputs, which includes, continuing the loop. So that's super fancy and would be at least like, okay, now, it can detect if it's in a loop. Um, but that still doesn't solve the case, which is not technically a loop in the sense that it would eventually run out. But where it's like you just have like a number that's incrementing forever. Now that will eventually overflow or like run you out of memory or something. Even though it's not actually gonna like never terminate. Um, but yeah, all of these cases I kind of feel like are probably just going to be in practice, like you just hit a build timeout and it's fine. Uh, so I'm trying not to worry too much about that. But there is kind of like stages of plans of like things we can do about it. One thing, there's like an obvious thing that Zig does, which I don't want to do, which is put a limit on like recursion limits. So you say like you can or loop limits where like you're like you can only do 10,000 iterations and then like if you do more than that in at compile time, we just kill it and we're just like, oh, sorry, error, like too bad. Because of course immediately where that leads is like someone's like, well, I have a legitimate use case where I need to do that much work. Are you telling me that like I can't move that to compile time? Like what the hell? It's valid rock code. Like it's gonna work if you just don't hit this arbitrary limit. At which point you get to like, okay. Well, we'll let you configure the recursion limit so you can like bump it up. And now it's just this chore for people to do where it's like, oh, it's like, well, yeah, sometimes it catches infinite loops, and then other times you're just like, oh, bump it, bump it, bump it, bump it, bump it. So I would rather just say like we don't put any limits in. But if you want to install an external timeout, which is probably a good idea anyway on your build servers, or you want to get this like notification of this thing's being slow, or maybe we do the super fancy thing if necessary. Those are all things I would prefer over putting in like a recursion limit or something like that. Anyway, that's a lot of detail about what is at baseline a pretty straightforward to understand feature, I hope. Other questions about compile time evaluation?
Yeah, what would be a use case for this feature?
So really, really basic, simple example is just like compiling regular expressions. So you got like the famous, mile-long regex for validating emails. You just say like, at the top level of your program, like, foo equals or whatever, like email, validate email equals that whole regex gets compiled at compile time. You don't have to like deal with like this is always an annoying thing in Elm is if you had one of those, it would fail if you had a syntax error in your regular expression, it would fail to compile when your program starts up as opposed to at build time. So in this version, it would get evaluated at build time and then cached and everything, but and so you'd actually get an error at compile time, like at build time, it would be like, hey, this regular expression is invalid. A much cooler example of that is I'm getting a little bit ahead of myself here, and I gotta keep an eye on time because I thought we'd be further along by now, but I guess I didn't. I got what I asked for when I said feel free to ask questions. Um, but basically, like custom numbers. So one of the pieces of feedback we've gotten over the years is that there are people who are like, I would really love to use Rock for scientific computing or data science or something like this, but they're like, I need custom number types. Like I need matrices and vectors, and they need to be represented differently from how people want them represented in games, which is another use case. And also I want like complex numbers and big ints and stuff like that. And all of these use cases, if you want them to be nice, you really kind of need to be able to do like operator overloading and like plus and whatnot. Um, what we've ended up with is a really cool system for not only can you define custom numbers like very easily in a way where it's like not even a separate language feature, it's just like the way the language works normally. Um, but also, you can write basically here is how to go from a flat list of digits before and after a decimal point to a try that says like either it's succeeded and I can fit all of those digits that I got in this custom number type of mine, or else here's an error saying like I'm sorry, this is an invalid literal. Um, so basically, what that means is that if I write, my custom, I don't know, vector matrix, whatever, scientific notation fancy thing, um, and I say like, actually, vector and matrix is a bad example for the what I'm thinking of here. I have like a complex number type, and I say my complex number type. I define it, blah blah blah, and I just want to say like I have a function that's defined using a my complex number type that takes one of them as an argument. I can just call that function passing like 7. Like I don't need to say like new my complex number type passing 7 as an argument. You just say 7. That's it. Just the plain old number 7. And at compile time, we'll do type inference and figure out, oh, this is a my custom number type thingy. Um, Here is how I create. I know how I create one of those using the thing I haven't talked about yet. Um, we call that at compile time, run your rock code that you defined for doing that. And if it's invalid, like let's say you have a custom number type that it's bounded in size, and you put in a literal that's gigantic and it's too big to fit in that number size. Um, you don't get a runtime crash. You get a compile time error that says like, hey, this number literal that you typed out is too big, and it's going to crash. If you were to run this code at runtime. So, but you don't have to run it. I'll tell you a compile time. And it's not just for number literals, but because of the compile time evaluation of constants we were talking about earlier, you could have like x equals, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever, like super long number, and then like y equals x plus 5. And since both of those are just depending on things that are available at compile time, both of those get evaluated and then run, and then you actually just get the error at compile time that tells you, hey, this is not going to work. Like you don't even have to run the program, and you'll get, the explanation at compile time that like this didn't work, and that's all based on like custom user space code. Um, so I don't know of any language that does all of those things, with the possible exception of it's conceivable that like in like Rust or maybe like C++ plus plus or Zig, you have oh no, sorry, Zig, you could definitely do it in Zig because of comp time. But like Rust or C++, I don't think you would be able to get that because unless you had like const fn's, like const functions that if you had sufficient const functions to do those things. But I'm actually not sure if they have the part where you could just use the number literal. I think you would still have to um, construct the number there. I wouldn't swear to it. I haven't thought about it that deeply, but definitely I don't know any functional languages where you could do that. To answer the question,
Yes, sir. Thank you.
cool. All right. Okay. So, moving on. So here's a quick summary of like the stuff we just talked about. So in Rock, you have like append, which is like, give me a list, give me a single element, I'll return you a new list. This is all conceptually mutable, but as a performance optimization, it might do mutation behind the scenes if the list is, never going to be used again, or never going to be, referenced again. Same thing with concat, and then readline. You can tell because it has a thick arrow instead of a thin arrow. That's how we know that there is a side effect happening. Um, so I'm mentioning this because the next section of what we're going to talk about, you might look at it and say, is this really a functional programming language? So I want to remind you, these are the semantics of the language. We do not have a concept of mutable values. Effects are represented in types, and we have a first class distinction between pure functions and effectual functions. We are as hardcore as Haskell is about this. Actually, arguably, you could say we're more hardcore about it because we don't have an unsafe perform IO. So basically, it's like you have the same concept of pure and effectful operations are clearly delineated in the type system. There's no exceptions. There's no getting around that. All values are semantically immutable. Really, I mean, could not be more of a functional programming language. Having said that, we do still want to be understandable and approachable and easy to get into if you're not coming from a FP background. If you're coming from an imperative background or an object-oriented background, which I guess is a subset of imperative, we still would like it to be a user-friendly language to you and for you to be able to use it and like be like, okay, I get it. The APIs are maybe a little bit different than I'm used to. Like maybe I'm used to having a push instead of an append where it's like mutating the thing in place, but I know how I can look at this and understand how append works. Um, so with that in mind, let's look at a well-beloved operator in the functional programming world, which is the pipe operator. I believe F# was the first language to use this operator with this syntax, but it certainly has caught on. Gleam has it, Elm has it. JavaScript has been for the past, I don't know, a long time kicking around some like various proposals for adding it. This is how it looks in Gleam. So you say I have names, which is a list. I pipe it to list.concat. So in Gleam, this list dot syntax refers to like list as a module. So in Elm, this would be list with a capital L, but in Gleam, they lowercase the module names. I'm basically saying this is basically a fully qualified function. So it's just a concat function passing in others with parentheses. So this is basically syntax sugar for just calling list got concat, passing names and others as the arguments to that. You can also pipe that to JSON.list, which is basically going to say I want to encode this as some JSON. So I've taken my names, I've concatenated some other names, I've turned all that into a JSON list of JSON strings, and then I say send, which is basically going to be like fire this off as an HTTP request. Let's say I have a function named send in scope. Fire it off to some endpoint, and they will receive my names concatenated with the others turned into a list of JSON strings. Okay, now in Rust, this would look pretty different. So in Rust, I would probably say send, and then I would pass to that. This is like macros in Rust end in exclamation points. So Rock, we use this for effects, but Rust uses it for macros. Any Rust function can just perform arbitrary side effects, just like in Gleam. And I would pass names dot into iter, because that's how you have to start if you want to do any kind of chaining. Any kind of like pipelining type stuff in Rust. Chain that to others dot iter dot flatten, collect with the turbofish of vec, and then close parens semicolon. People tell me Rust is great at functional programming. I don't get it. Like I'm used to this kind of thing, and I look at this and I'm like, yeah, I mean, kinda. But like to me, one of the things that's super nice about functional programming languages is the pipe thing. It's like all of the functions and the APIs are very much designed to be like, give me the thing, give me some information about what you want to change about that thing, and I'll return another copy of the thing immutably. There's no like ampersand mut. There's no like push, take the thing, mutate it in place. It's all just done by, argument in, additional arguments as necessary, and then return, the first thing that you gave me as the argument out, which is how you get this really nice pipelining thing. In Rust, you just very often have this like, well, I need to like nest these, but I can chain these together using methods in the middle, but not the outer ones. And then send, of course, can't be done that way. I don't know. It's just never felt like trying to do actual what I consider to be functional programming in Rust is like that ergonomic because of this, because the Rust APIs are not, and Rust as a language is not really set up for this pipe kind of experience. In the new version of Rock, though, you can do it like this. Names.concat others.encode JSON.string arrow send. Okay, so I want to make some observations about this. One is that if I were a JavaScript programmer, aside from this part right here, I would probably look at this and be like, yeah, that all makes sense. Okay, maybe I'd say like exclamation point. I don't know what that is. If I were a Ruby programmer, I might be like, oh yeah, sure. Because Ruby actually has a convention of using exclamation point at the end of method names to mean this thing does destructive updates. It's not quite the same as side effects. It's like for more about mutation, but they're kind of like in a similar vein. And we did actually take direct inspiration from Ruby on the choosing that convention for this. But when I mentioned about like getting making a language that is approachable to people coming from an imperative background, I like that this has the pipe aspect of Gleam. It's just like you can read it from start to finish as like we started off with names. We concatenate it others, just like in the Gleam one, names, concatenate others. Then we're encoding it as a string, like JSON string. So Gleam would call it JSON.list. We're calling it .encode, JSON.string, JSON.stir, and then finally give it to our arbitrary local scope function of send, which in Rust, they don't have an equivalent of that. So there is a distinction between the way that we're using dot here and this arrow. Basically, the arrow just means like it's literally the same thing as pipe in Gleam. So we used to have this syntax, but we changed it to this basically because we now have this sort of method chaining kind of style, which I'm going to explain the semantics of in a sec. Um, and the purpose of this is basically just to be like, yeah, I just want to call this as a function. Like everything before the arrow becomes the first argument to what you're calling here, and then everything inside these parentheses just becomes like additional arguments after that. So this is just the pipe operator. The reason we did it, change the syntax from pipe to arrow, this is like C and I guess C++ also use this, is essentially that it looks weird when you're mixing and matching these to have a pipe like this because you're like, wait a minute, does the dot that like if I kept going with dots and other things over here, it's like, what's the precedence of this? Like it kind of feels like the pipe always feels like it's sort of creating its own sort of standalone thing. Like these dots in here clearly don't go with the previous pipes. So whereas in this case, there's a lot of precedent for using that in that style to mean like this works the same way as a dot.
So
We actually got
is
that from ReasonML. ReasonML does the same thing. Yeah.
so is encode, is that a that's not a function on lists. Is that a function on like everything? Is it like a function that can be applied to anything? It just takes self comma JSON string. It's like a polymorphism, like a what do you call it? A multiple
Yes.
dispatch
So
kind of thing.
yeah, it is on list, and we are going to talk about that.
Okay. Oh, it's
And
on
yes, it
list. Oh,
is.
so it's a method on list.
Yes.
Okay. Is
Um,
it a method also like on numbers and
yep.
strings? Okay. Okay.
Mhm.
Okay.
Yeah. So what this is saying in our case, this is actually a little bit different from what Gleam is saying.
Hmm.
This is basically saying I want this entire thing to be encoded as a JSON string, as opposed to like you could say, give me like some JSON like UTF-16 bytes or something like that. There's like different ways you could encode
Because
JSON at like different string encodings.
because
Um,
Gleam is really using currying there, right? Like they've got a JSON list, takes JSON string as a function.
ah,
It's
um,
plugging the JSON string, like right, because it's totally different. Because this is that a so JSON dot string, that's not a function in that encode. That's a
correct.
type
Yeah.
notation or something.
JSON.string would be a value. It would probably be a value of type encoder, is my
Yeah,
guess.
yeah, yeah, yeah.
Um,
Right. Yeah, that's what I mean. So yeah, it's not a function, but it's okay. But
right. And
it's
and so this pipe is because Gleam isn't curried, what it
mhm,
does is it basically says like I'm gonna take this thing right here and I'm
mhm.
gonna just basically stick this as the first argument here and just kind of bump the others out of the way. I think Gleam does it
Oh, okay.
argument first.
Okay, that makes
Elm
sense.
Elm does it with this becomes the last argument instead of the first argument because it is curried and that's the natural way to implement it if you're doing that.
Mhm.
And I think F sharp does it that way too. But
Yeah, F sharp's the last one, but so okay, so this one actually is it's bumping it. Okay, so that makes sense. So it's not
yeah,
curried, but it's just applying it as the first argument,
yes,
and then that dot encode, that's just a method that takes a is JSON.string. That's not an encoder. That's like a
it's a encoding format is what we call it.
okay,
But yeah, it's
okay,
it's
sure,
also
sure,
not
sure.
a function. Yeah, it's just a value.
Okay. And then
Um,
every object has a dot encode, or everything has a dot encode in
yes, they're not
Rock.
objects, but
Or no,
most
I'm
things
sorry.
do.
Yes, any
Yes.
type
But they look
or
like them, right? That's why I had this
yeah,
slide.
I know
I was like,
it's hard to
remember,
lose.
remember, remember the semantics, right?
Yeah, yeah, yeah,
So,
yeah,
but it,
exactly.
but it looks like if you're coming from an object-oriented background, this looks really familiar, right? I didn't even have to
Hmm.
tell you what this was called, and you're like, so that's a method, right? And I'm like, yeah, that is. At first, I was like, let's not call them methods, let's call them something else. And finally, I was like, no, let's just call them methods. Like everybody who looks at this is like, that's a method, right? And I'm like, yeah, let's just lean into that. Well, sure, we'll call them methods.
Because
um,
some languages have like mix-in methods where you have
right,
like
right,
you define like a static. Well, I mean, like from like C sharp or something, you define like a static type, and it takes
right.
self as the first argument. So it's
Mhm.
kind of similar to that too. And like
Rust does that too, yeah.
yeah, yeah.
So Rust is also not object oriented, but Rust, yes,
Mhm.
and in Rust these are called methods too.
Okay.
Yeah, well, let's dive into this a little bit more. Yeah, so this one, like I mentioned, this is just a plain syntax trigger for a function call. It's just like, if you have some function that takes arg1, arg2, and arg3, in Gleam, you would say like arg1 piped to some function arg2, arg3. These two are exactly the same. Like they're literally there's no difference other than syntax. It's just one's completely syntax trigger for the other. And it's the same thing in Rock, except we just do with the arrow instead of the pipe. It's just like, yeah, exact same thing. There's no difference here whatsoever. The compiler just discards that distinction immediately and desugar's one into the other. So this is just a syntax for calling this. Now that we have this in Rock, like my day job is programming Rust at Zed. I am all the time running into this and being like, oh, I wish we had this in Rust. It's really nice. It's like it's nice to be able to just like you're doing a bunch of stuff and you're just like, oh, I just want to like throw in a function that I defined locally. It's not a method. It's just like I just defined it locally in scope. I sure would love to just throw that in the chain. I was like, no, no, now you gotta like put this all the way at the front and disrupt the whole flow of what you're reading. And then like after that, try to pick up the chain after that again and like jump back to it's like just yeah, it's nice. Just call a function, whatever you want, wherever in the chain. Okay, now this first thing, this is the part where we get into like what looks like, Rock has become an object-oriented language, which of course it hasn't, but it does look like, like you said, it's a method call. Um, so first thing to note is that this is partially syntax sugar and partially something semantic. So this is just calling a function called concat, and it is doing the same kind of thing that that arrow is doing and that the pipe operator does, where it just takes this name and just sticks it as the first argument. So this is something important to note because in a lot of object-oriented languages, when you have a method call, you don't actually get a separate argument. You get like a magical this or something like that, where you just like refer to it in the body of the function, and it's just sort of like implicitly there. We're going more of the route of like Rust, or I think Python does this too, where it's like, yeah, that's just the first argument is when you're calling it in this style, it's the thing before the dot. That's what comes in as the first argument. And when you're defining this thing, you just define it as a completely plain function. It's just like I have a function named concat. The first argument is something, some particular value, and as we'll see a little bit later, I can define this in a way where I'm supporting this syntax for calling this concat function. But this is still a completely plain first class normal function. I can pass this to a higher order function. I can return it, whatever. The function itself is completely normal. I'm just going to be doing something a little bit different to say I want to associate this function with, in this case, it would be the list type. Okay. Um, so the fully qualified version of this would be list.concat because this is a function on the list type. So if I wanted to, I could say list.concat names others, and that would do exactly the same thing as this code in the box. Like no difference whatsoever. I can either call it in this method style or I can call it fully qualified style. Just say list.concat passing names and others. Absolutely no difference between the two. Um, the full type of this function is it takes a list of A and a list of A and returns a list of A. So this is again like in contrast to in some languages you have like, oh, this would say self, or this would say like this or something like that. It's like, nope, it's just again, plain function, list of A, list of A, list of A. If you're passing this around to other functions, they don't know or care that this function happens to be associated with the list type. It's like, yeah, that's an irrelevant distinction. The only way that it matters that it's associated with this is very, very specifically if you're calling it in the method style. As we're going to see, that has like semantic implications. It's not just how the code looks, it's how the code works. Um, okay, so names in this case is going to be a list. Names is more specifically a list of strings. And so the way that Rock knows like what concat function to call is just that basically we have type inference, we have full type inference, which means that like the compiler understands the types of everything in your program, even if you don't write a single type annotation anywhere. It knows from type inference that names is a list of strings. And so when you say dot, like whatever comes out after that, like this concat thing, it's just going to say, oh, well, this is a list. So, okay, list dot concat. That's it. It just says like I use type inference to figure out that the type of names is list. Therefore, this concat must refer to list dot concat. So we just literally go look up on the list type and say, hey, list type, what is your associated concat function? Oh, that's what's being called here. Again, passing the thing before the dot as the first argument to it. So, oh yeah, and that thing just becomes the first argument to concat. So this is the technical term for what we're doing here is called static dispatch. Dispatch meaning basically figuring out which function to call, and static being we're answering that question statically at compile time. Dynamic dispatch would be if you're doing this at runtime. So you have languages which support that. Actually, a lot of languages that support static dispatch also support dynamic dispatch. So this would be where like you have dynamic types and the types can change at runtime, or maybe you can like change the methods at runtime. We don't support dynamic dispatch at all by design. This is only static dispatch. And we actually get some benefits out of that. Like there's performance benefits because you don't have to do any work at runtime. It's all done at compile time. Like by the time you get to like building your actual, like compiling the Rock program to its output binary, it is as if you had written list.concat. Like it is a plain ordinary function call. There's no lookups at runtime, no fanciness. It's just like, it's all resolved at compile time. Just like it is in Rust, for example, or C++. Having said that, actually, no, sorry, C++ is a bad example because you have like other fanciness that has more runtime costs sometimes. But yes, like Rust. But because we're doing all this statically and we have type inference, we can do some stuff that's literally not possible to do using only runtime information. You have to use static type information if you want to do some of the things I'm going to show you in a little bit. Um, so the procedure here, just to recap, first you infer the type before the dot. So in this case, names has the type list of strings. You call the associated function on that type. So in Rock, we now have a explicit concept of saying when I'm defining my type, I can just associate certain functions with them. The functions themselves are just plain, ordinary, vanilla lambdas, but you can just say this plain, ordinary, vanilla lambda is associated with this name on this type. So list.concat is basically saying like, hey, this lambda that I wrote out, when I'm doing static dispatch like this, I'm doing a method call. This is the one, this is the lambda you should call. And then the value before the dot becomes the first argument to the lambda, and that's all there is to it. So now you know everything there is to know about how static dispatch works in Rock. That's it. But there's a lot of really, really cool implications of stuff you can do with this. Let's look at one. So associated functions are basically our way of saying
Oh,
of doing.
wait, sorry.
Oh yeah, go
One
ahead.
more question. So why do you need that arrow to send? Like, could you just have that be like a dot send bang,
Ah,
or is that?
so I'm assuming here in send. So if I did dot send, that would mean that. So here I've like encoded this as a JSON string.
Mhm.
At that point, I would assume that it would either be, I guess, depending on. Well, all right. Let's just assume for simplicity's sake that now at this point I have a string.
Oh, but that's what I was assuming, but
Yeah, sure.
that may not be true.
So
Yeah.
so let's at this point let's would it make sense for string in Rock Standard Library to have a like
Oh,
send
I see. So
method,
it's a
right?
module issue. Like it's sort of
Exactly
in a
right. It's
different
like so
module. Okay, that makes sense. Yeah,
this
yeah,
is
yeah.
like a I just wrote this like
Sure, sure,
right
sure.
above this in my code, right? That's the cool part about it is it's like you can use dot for the static dispatch, but if this is more like local dispatch, it's like just plain
Sure.
old function call and
Of
scope.
course. Okay, thanks. That makes
Cool.
sense.
Um, okay, yeah. So there are ways to do things like this in different languages. So, like in Haskell, you would have type classes. So you could have, famously, you have like monad and monoid and functor and stuff like that. Um, we don't have those because you don't need to formally define like, oh, this is like a concatenable or something like that. It's like, no, you just say list has a concat function and then like anybody can call that. There's no like I have to classify this as being a monad, a monoid, a functor, a semigroup, whatever. PureScript really went ham on those. It's got like ring and like semi-ring and you don't need to do any of that. Like Rust has like impl blocks and I guess like traits would be the kind of the more type classy way. In Rust, impl blocks you can do to get this method style without classifying. So you don't have to, like, you can just say my custom type is having a method called concat, but impl blocks in Rust don't let you like abstract over that. Like you can't say, for example, in Rust, um, give me I'm going to take some sort of type. I don't know anything about this type other than that it has a concat method with the following signature or the following sort of constraints to it. And I would like to call it. In Rock, you can do that for any method you like. You can just say like this is a function, and it takes something like that has a concat method, and I'm going to pass this particular thing to that concat method. And if you pass something to me that satisfies that, then cool, I just work. Rust impl blocks don't give you that. You have to be more formal about it and define a trait in Rust, which is more like a type class in Haskell. So in Rock, you don't need to be formal about that. You can just be like anybody who has this, you can just do that. Like you don't need they don't need to have opted into like I declared myself to be concatenable. You can just be like, oh, do you happen to have this? Cool. Then you work with this. You just work, even if you didn't think ahead of time that you needed to classify yourself as such. Um, and of course, classes in OOP sort of do more than this. Like classes are usually about like I mean they don't have to be, but they're usually about like storing some mutable state, and then you have objects which have like references, which is like a first class concept at runtime. We don't have a concept of like references or reference equality in the language. Um, this is all just like it is what it is. It's just the stuff that I just described here and nothing more. Um, okay. Now, because this is all done sort of anonymously and you don't have to define it up front, you really can just write a lambda. By the way, this is our lambda syntax. This is also taken from either Ruby or Rust. I think Rust got it from Ruby, and I think Ruby maybe took inspiration from Smalltalk, if I remember right, for this sort of pipe space syntax for lambdas. But it's basically like this is like a lambda. It takes two arguments. First one's named, second one's named more. Names.concat more. Um, the inferred type of this will be this takes a type variable named arg1 because remember if you just like put this into the rocks REPL, it's just going to say like you haven't told me anything about any of the types here. All I know is that arg1 has a method named concat, like whatever the first argument is, and that concat method takes whatever an arg1 is and an arg2 and then returns this return value. So this is an example of like you can just write whatever you want here, and the compiler is going to infer, okay, these are sort of like the constraints of what you put in here, and any type that you give me, like any value that you give me, as long as its type has a concat method with these types to it, we're good. We're all set. That's all there is to it. So with that in mind, you get this sort of anonymous, like structural ad hoc polymorphism. Now we can use that to give a concrete example of why this is cool in this encode function. So remember we talked earlier about like list.concat is like, give me two lists and I return another list. So when I call this, I'm getting back a list and then list has an encode on it. So list.encode is basically give me a list of whatever your element type is because it's polymorphic over that. Give me a format and we'll see what that thing is about later. And then I will give you back a string. I'm oversimplifying right now and calling it a string. We're going to make it a little bit fancier in a sec. So the where clause on this, which basically describes like what are the static dispatch constraints, like the method constraints. I'm saying, okay, well, your element type also needs to have encode because if you give me a bunch of elements and they're not encodable, then like I don't know how to encode them. So they need to be encodable using the same format type that you gave me here. So if I pass in JSON.str, you need to be able to, this only works if whatever your list's element type is also supports a format of that same type. Because I'm going to call it on each of the elements, right? And then format needs to have an encoding format. So this syntax here is basically saying like, it's kind of like I have a series of constraints and I want to describe them without having to repeat them every single time. So this is kind of like now we're getting into something that sort of looks like a Haskell trait, but it's more like a type alias. So this encoding format thing will basically be like um, defined as like, oh, I have like, okay, whatever my format thing is has a here's how to format a string, and that means give me a string, and I'll give you this output type, and then sorry, I'll give you a function that takes the output that we've built up so far, and then the same formatting thing as before, and then I'll return the new output with this string appended to it. And then if it's a bool, then I take in the bool and I give you back a function that's like, okay, take this output and the format again, and then I'll append that bool to the output, and so on and so forth. Don't worry if you didn't understand any of that. The point that I wanted to make here is just that using this combination of things, I can completely describe that list.encode, the way that it works is you give me a list of elements, you give me a format like JSON.string. Inside that format value that you pass me, so in this kind, this JSON.str, exists all of the logic for how to format whatever you want to give me. So it's like, hey, if you gave me some strings, I know how to do that. If you gave me some bools, I know how to do that. If we kept looking at this dot dot dot, like what this would include is like strings, bools, lists, all the stuff in the rock standard library, plus records of these, plus tuples of these, plus tag unions, which is our sort of sum type or algebraic data type of these. And basically, the encoding format comprehensively describes, including recursively with combinations of collections of these, like every single type of rock value you could possibly get. And as long as you're able to provide one of these formats and then a list that knows how to do this encode, you're all set. So now I can just call .encode on my list, just pass in a format, and using all this static dispatch stuff we've been talking about, we can now end up with just a string on the other side. And as the caller of this code, I have to do almost no work at all. I don't need to like, know how encode works. I don't need to know how JSON that string works. I don't even need to like necessarily know how all of these types work. All I really care about is like if I'm a beginner and I'm just like learning this for the first time, I'm just like, yeah, I don't know. I just like encoded it and I told it what format I wanted to encode it in, and like it did it. Yay! With full type safety. Um, now, the really cool part about this is that because this is done doing using static dispatch, we can do exactly the same thing for decoding. So I can say like this is how I would encode some JSON. Decoding JSON is just as easy. I can say I have some big JSON string, just a bunch of raw JSON. I can call dot decode on that string, passing JSON.stir as like, oh, this is a JSON string that's coming in here. I would like to decode that JSON string. And then I basically just get back on the other side, miraculously, my users. So like if this JSON string has you know, a bunch of JavaScript or sorry, JSON objects of users in it, I will just get those back here. I'll explain the question mark in a second. That has to do with dealing with the try, or like in Rust it would be result, or OCaml, or in Haskell it would be either. Um, but I mentioned earlier that when I was teaching beginners Elm, uh, learning how to do JSON decoding was the number one thing. Like currying was number two, but number one thing that beginners all struggled with was how to do JSON decoding correctly. The learning curve on this is like zero. It's basically as convenient as JavaScript's JSON.parse, but with none of the footguns. This has complete type safety, believe it or not. I know it doesn't look like it, but like if your users thing right here um, does not actually fit the schema of the JSON. Like for example, if the JSON is like, um, uh, I have, let's say the JSON is just like a number. Like you have a JSON that's like 42, and users is like, oh, I'm a list of records, and they have first name and last name and email. This will actually give you at runtime a just like immediately right here, it will say, I failed to decode. I'm sorry. This did not fit your schema. And the schema was inferred just using type inference on users. And the really cool part about this is not just that it's like a type safe JSON.parse from JavaScript, but it's that everything that is required to implement this is all the stuff I just talked about. Like there's zero new language features that are required for you to understand to know how this works. So here's how it works. So we had list.encode. Here's stir.decode. Takes a string and again, format. So this is the JSON.stir that says like, what are we decoding it as? Like, oh, it's JSON as opposed to like XML or CSV, or whatever the format it might be encoded as. And then we have our goal. So this goal type is basically like, with encode, it was like this is the output, like this is what we're serializing to. Well, goal is like what are we deserializing to, right? This is like what comes out on the other side, this users here. Um, so the where clause here is just like goal needs to have a decode. I'm just saying like, yeah, the goal type, like users needs to have a decode method. And decode takes a string and I used result here. That should have been try, my bad. um, but basically it's like I'm taking decode is like needs to be able to say, okay, if you give me a string, because I'm decoding a string here, and I have the same format type, give me back a result of, oh, like was it decoded successfully or not? And then you have the same format thing with decoding format. Um, so uh, the actual versions of these are a little bit fancier. So you actually do have like goal is a this would be wrapped up in a try. Like it wouldn't actually be like literally just I give you back the value all the time. It would be like there's an error here, like there is here. That would be propagated up here. I'm like oversimplifying a little bit of what the actual API looks like. But the point is just that encode and decode use this static dispatch in exactly the same way to be able to say, I would like to encode this thing using this format, or I'd like to decode this thing using this format. And then because it's all static, you get to incorporate type inference into all of this. If you tried to implement this type safe decoding thing in a dynamically typed language that's using dynamic dispatch, it's just impossible because at the point where your, let's say, runtime interpreter is running this, you don't know what the type you're decoding into is yet. You haven't executed that part of the program yet. You can't be like, oh, what's the schema of users? It's like, well, I don't know. I haven't created users yet. But because Rock is doing type analysis on your entire program well before runtime, we can use static dispatch to say, oh, I know what the type of this thing is. I know what the type of goal is way before this function runs. And not only can I check that all these constraints are satisfied, but actually I can just go find goals decode method at compile time and just substitute it in. So by the time we get here, whatever users like list, it's going to be a list, and then list has decode, and then decode inside of list is going to of course have the like elem dot decode, and elem is going to be user, and user is going to have its own decode. All of that just gets slotted in here at compile time. So encode and decode in Rock are basically just like as trivial as they are in JavaScript. Like in JavaScript, you have JSON.parse and you have JSON.stringify. Um, they're as trivial to use, but they're completely type safe. Whereas in JavaScript, they're just, well, I mean, both of the encoders are safe. But in JavaScript, like JSON.parse, even in TypeScript, is notoriously just wildly unsafe. And as soon as you wanted to make it not wildly unsafe, you have these libraries like Zod and whatnot in the TypeScript world, which basically just draw you into the Elm approach, which is totally type safe, but also has a huge learning curve. So one of the things that static dispatch has gotten for us is it's one very simple system that's easy to learn, and like maybe the implications are tricky. This is like the most hardcore use of static dispatch I'm aware of, is this encoding and decoding thing. So apologies for the drink from the fire hose. And if you didn't understand what these types mean, I totally understand it. Don't worry about it. But the point is just that this one language feature is so much more than how this code reads. It's about being able to have an easier beginner learning curve, regardless of your background, for like decoding, for and there's other like more powerful things than this that we can do. But basically, it's one simple language feature that's very, very, very powerful. Um, I'm gonna kind of like,
Richard,
oh, sorry, go ahead.
one question, if you don't mind.
Yeah.
I was curious how, in practice, writing rock code, this sort of ad hoc approach to sort of interfaces or type classes or whatever has been working out, because I understand that sort of just having the right associated functions and having all the types work out, that's sort of like one part of it. But say if I wanted to write a generic function that works over, I think you used examples of like monoids and semigroups and stuff like that. I want to write something that works over all of those. Just having the types work out isn't really enough. Like I need the underlying guarantees that if I do like say certain compositions of those functions, like I get a particular result. And I was just curious if there's any ambiguity, like concat could mean a lot of different things in different contexts and maybe still have the type that checks out. Is that ever
Yeah.
really a problem in practice?
So the direct answer is we don't know yet because the compiler's like not even totally usable yet. So um, all of the stuff that's on this slide, in theory, like I could probably write a test in the compiler. It's like, oh yeah, all of this works, and I would probably expect it to work. Like the static dispatch stuff is all implemented in the compiler, but we don't have enough of the like standard library. There's a bunch of missing pieces before you can actually write like any kind of interesting rock program. So I can't directly say we know. The reason I have confidence that it's not going to be a problem is that Go has kind of already done that experiment for us. So Go's interfaces, this is pretty much exactly how they work. They're just like, yeah, if the names and the types line up, you're good to go, and you can just do whatever abstracting over those however you want. And there's a ton of Go programs out there and a ton of Go programmers. People complain about a lot of things in Go. Um, I have not, and I actually asked several like, you know, people who've done professional Go, like, is this a problem in practice? Like, do you get something where it's like people chose the name like, and they like didn't, it looked like it was going to work and the types fit, but it actually didn't quite follow the semantics you wanted. And they're like, no, it's not a problem. I think part of the reason for that is that you just end up with in practice like people are aware of like what the comp like if I have a method named in code, people kind of know like, yeah, these are the semantics of that. And for you to end up with something that would have like by sheer coincidence the same name and exactly the same types that works out, and then somebody uses it by mistake and like it gets a surprising wrong answer. It's like in theory that could happen, but it seems like in practice it just doesn't happen. So I think it's a valid concern, but I think we have good reason from the lots and lots of data points of Go doing the same style of abstraction, and seeing, and apparently it's actually like Go people consider it a selling point of the language that like Go has this like structural ad hoc polymorphism where you don't have to define it up front and you can define it after the fact. Um, Like you don't need everyone to like explicitly opt into participating in this. You can just be like, oh, this thing works and that thing works. Actually, literally, it already came up in Rust. Like since we did this, I was doing this at work and I wished we had it. There was um, a function I wanted to write that was abstracting over uh, two different things from like a third party thing that I don't have control over, so I couldn't add it to their trait. I couldn't add it to their impl blocks to support what I wanted. But they did have like the same names and the same semantics and the same and the types sort of lined up. So I in Rock I could have written that function, but in Rust that was impossible. So I understand. I got a little taste of like what Go programmers are talking about. Like, oh yeah, it's nice. And again, apparently they say it's not a problem in practice, but we won't really know until like you can actually build significant programs with this. Every programming language is ultimately an experiment. We have good reason to believe that this is going to work out nicely, based on the precedent of Go and other reasons. But you never really know until you try it. So I can't claim overconfidence and be like, oh yeah, no, it's definitely like I can't reassure you it's 100% for sure going to be fine. The best I can say is like we have really good reasons to think it's going to be fine, but we're going to find out in practice once the compiler's all the way there, and you can actually build interesting rock programs with this.
It was helpful. Thank you.
Totally. Um, yeah, okay, cool. So one other thing that I want to note that's like kind of a cool use of this, and I'm going to wrap this up quickly so we can look at some larger code examples. Um, I mentioned the last time I was used a functional programming user group that we are intentionally adding for loops to the language, partially because it's nice for people who are coming from an imperative background, but also because even as an advanced functional programmer, I have to admit, however grudgingly, that sometimes a for loop is just the best tool for the job. Even though I know I'm like completely comfortable with fold, reduce, whatever you want to call it, I'm completely comfortable with recursion. Sometimes there's a for loop with a with a variable you can reassign out of it just is the nicest
As the
way to do it.
organizer, I just have to cancel this meeting of the Houston Functional Programming
All right,
User
well, it's been real.
Group.
See you,
I'm
everybody.
really, yeah, sorry for everyone coming here. I'm just, yeah.
I had a Jose Valim who created Elixir on Software Unscripted, which is my podcast a while back, and we were talking about how we want to add this to Rock, and he's said the same thing, which is like he wants to add for loops to Elixir, but for whatever some Elixir specific reasons, it's been hard to make a design that makes sense. But also every time he brings it up, people are like acting like he's like a sleeper agent for imperative programmers, even though he created the language. It's pretty funny. Anyway, um, but yeah, this is a cool example, I think, of just like because we have this, we can basically say you can do like for cat in cats and just have that be the syntax. We don't need to make you write out cats.iter because we can just say, oh, well, just whatever you put there just has a constraint of like it needs to have a .iter function, which like you call it to like iterate over the thing. To give me back an iterator lets me, step through it. You can also do cool things like because we have this like .encode thing that takes a JSON.stir, you can pass in like a modified version of this. So you can say, I want to encode this as JSON where I have camel cased all the fields. Like I'm giving you snake case because that's kind of the style in Rock, like big underscore JSON underscore stir. But the thing that I'm sending this to is expecting camel case fields. So just while you're encoding it, just go ahead and do that. I use this as an example though, because this is a pretty cool thing that came out of static dispatch is like, it's actually pretty convenient for when you want to have like really concise configuration options. So the old way we would have done this, we would say, okay, JSON.stir is a function that takes a record of your different configuration options. So maybe you want to say like camel case fields and also like I don't know, exclude this field or exclude that field or something like that, like filter, to do the fields. These are all sort of optional configurations you might want to do. As it turns out, this static dispatch like chain style of calling is just like a really nice way of doing that. That means that you don't need to have a concept of, or like you don't need to have a more verbose style of like doing it with records. You can just be like, yeah, just take this normal JSON.stir thing and just like customize it. And this returns you back a modified JSON.stir that has, internally it's got the like camel case these things, right? Set. Um,
Can I ask a quick
yeah,
question? It's a compiler question. I know I'm,
sure.
but so if you were to implement encode on a custom type or something like that, would the compiler warn you that it's this encode is like a reserved word for JSON? No, I'm
No.
just curious. I'm it like Is that, or is that something that you just sort of expect that, I know I'm assuming dot encode with JSON string. I mean, probably it's just making sure that that module has a dot encode with that signature, which is totally fine. But I was wondering if
Yeah.
there's any enforcement of like standard, like iter, for
No.
example. You wouldn't want to implement iter and then try to do a for loop and then have it
Right.
be like crazy.
Yeah, the plan is not to do that.
Okay.
Again, just following Go's example of like if it had been necessary in Go, people would have clamored for it and they could have,
Oh, okay. Yeah, that
added
makes
that
sense.
or like done linting, for something like that. Since it seems like it's not a problem in practice, I'm assuming we won't need it. But totally reasonable question. Um, yeah, so another cool example of this is you can just have like syntax sugar for operators. So like double equals in Rock will now desugar to. Actually, I decided to change it to is eq, but didn't update the slide. Basically, it's just like yeah, you support equals. Just add a method that's named equals, or eq or is eq, whatever we decide on. And there you go. That's how double equals works, right? And how do you support custom equality? Literally, just write the function, just with that name. That's it. And then that's also how you get into custom number types. So going back to what I was saying earlier, but the compile time execution of pure functions, literally a plus b, and this is, well, okay, I have a pull request that's not landed yet, but it's almost the case that literally when you write a plus b, it's literally just syntax sugar for a dot plus b. So if you want to make a custom number type that supports its own plus operations, just write plus as the name of your function, and you're done. That's it. Um, I know that this is a thing people can therefore use to do funky DSLs. I'm not usually a fan of those. Like you could, for example, use like division to be like, ooh, I'm making a URL thing, and now slash means like a pen. Like I'm not going to tell you you can't do that, but I'm saying I wouldn't choose to do that, even though you could. Um, we talked about that as like a downside of doing it in this way, but again, we kind of come back to like Rock is designed to be a language that's usable in a lot of use cases. I like to call it the long tail of domains. And it is important to me that people who want to use Rock for something like scientific computing or data science or whatever, or game programming where they want their own custom number stuff, that they can do these things like they can implement their own custom numbers. And I've ended up coming down on the side of like, since that's kind of like the goal of the language, that even if there are some uses of this that I wouldn't personally choose to do, it's it's worth it to be able to unlock those use cases where people are like, yeah, if I can't do this, and I have been persuaded by people that like this is actually very important if you're doing like number stuff. Um, Okay. We talked about this a little bit earlier, but like, yeah, this sort of like long number I'm making a custom, thing. Literally, you just have to say like, I have a method, an associated function called from digits, and it's just like, give me a list of digits, and I will give you back the number. Again, this type is a little bit more complicated than that. I'm kind of oversimplifying here for slide purposes. But that's the basic idea. It's like you like literally if you want to be able to have there be a number literal, and that number literal will turn into just magically turn into whatever my custom number type is without my having to say my big num dot new or whatever. It's just like you just use it and it's fine. You just use the number literals like you would with any other number literal. All you got to do is implement a from digits method and you're done. That's it. That's how you make a custom number type in Rock. And yeah, if you want to support plus, then you implement a plus, and if you want to support equals, you implement equals, and greater than, less than, etc. But again, like all of these things are really like all I've been doing for the past like N slides is like I explained this, and then I've just been showing you implications of what you can do with that. Um, so I know that like if you look at this, you might be like, oh, the reason that you're doing this syntax is just to make it so that JavaScript programmers can get into Rock more easily. But to me, that's actually like several levels down the list of like what's awesome about this. Really, what's awesome about it, in my mind, is it's like this one simple concept. And I just like I'm teaching you the syntax for it. It's like look at all these things you can do with just this one thing. And again, I want to contrast this with like nominal ad hoc polymorphism, which is what like Rust and Haskell and them do. You would have to say like, okay, this is like I have to explicitly say I have a concept of a from digits trait or an iterable trait or an eq trait or an add trait. You do end up with like a lot of these like these all have to be defined somewhere. And like in Rust, you just have like trait soup if you want to make a custom number type. In Rock, you don't have to say any of that. You just literally just write them. Just write the methods and you're done. Um, Besides the sort of like ceremony aspect of that, something that I absolutely love about this is what it does to the documentation and sort of the conceptual structure of your rock code base. So in rock, if I've got lists and I've got concat, get, and replace, let's say, um, this is it. It's like you have concat, which is like I forgot to change this to update the syntax to this to the parentheses. These are the old docs from the website. But it's like, hey, put two lists together. This is what it does. It's just like give me two lists of elements, and I'll give you back a list of elements. Um, in Elm, it's the same thing. Like it's you can guess where we got the, the idea for the description of this, right? Because Rock's a direct descendant of Elm. Uh, Take two lists, put them together. The only difference is that the Elm one is curried. If you pull up the Elm documentation, again, it's just like this. You have lists, you have a flat list of the operations that go with it. In Rock, this is more formalized now. So it's like list is a type. These are the associated functions with that type. In Elm, it would be like list is a module, and these are the functions inside that module. But it's the same basic idea. Like you'll see list, and then just like here they all are. That's it. Oh, like here's all the list stuff. In contrast, if I look at like Rust, like where does the equivalent of concat and Rust come from? It's like, okay, you have extend, which takes an into iterator. That's like fair enough. This is just like a distinction of like they take an iterable rather than like a list. Um, but it's like, yeah, you have this trait. I'm saying, oh, I'm implementing the extend trait, which has, and I also have like extend, two different variations of extend, so you can like implement the trait in multiple ways. We don't have that because again, there's no trait concept. I have all these like froms for all these different things. Whenever I'm reading Rust docs, which I do on a pretty regular basis because I work in Rust all day, um, it's just never as straightforward as it is in Rock or Elm, where it's just like, yeah, it's just like, here's your list. Here's all the list stuff. It's like, but what about how does equality work on a list? It's like the function's called equals. Just scroll down until you get to equals. That's how equality works on lists, you know? If you're looking at a number type, it's like, how does it do? Like, how does plus work? Just search for PLUS. It's right there in the list, right? It's a flat list. Here is all the stuff that list supports, all the operations that work on lists. You don't need to like have this layer of indirection where it's like, well, some of them are directly on there, and then some of them come from a trait, and then like, um, this to me is a downside of nominal ad hoc polymorphism. It's the same thing in Haskell. You get this categorization, like this is Rust docs again, where it's like trait implementations, blanket implementations, the plain old ordinary stuff. It's like I would just rather have the structural thing where it's like, yeah, here's the list. That's it. It's just I have this thing. It's called a list. Here's all the operations that it supports, all the associated functions. That's it. There is no categorization of like where these things come from. It's just a plain flat list. Um, Rock used to have a nominal ad hoc polymorphism system called abilities, which we got rid of in favor of static dispatch. And this makes me really happy because this was something that I always loved about Elm is that reading Elm docs is so simple and straightforward. There's no like chasing stuff down and being like, oh, wait, an into of that thing? It's like, no, it's just here they are. They're right here. There's no like extra source of information on what it supports. It's all just in one place. Um, oh yeah, and here's the the Haskell equivalent, right? You have like eq1, ord1, read, show, alternative, applicative, functor, monad, right? All those classic ones. And again, it's like nope, no instances, just here they are. One other thing that I love about this, and this is the last thing I'll say about the ad hoc polymorphism, is instead of classifying things like, you're like, oh, is this an applicative? Is it a functor? Is it a monad? Or if you're in the pure script realm, is it a semi-group? Is it a semi-ring? Is it a ring? You just focus on API design. You're just like, what do I want to expose? These are the operations that I think lists should have, and that's it. I love that because I think that is a much better focus to have. Is just like, what are the operations? What is their shape? What's the type of these functions? What do they take as arguments? What do they return? What does that allow you to do with the list? Like what's supported, what's not? That's hard enough on its own without also adding the additional thing of like, and like, do I want to classify this? Like, should this be a functor, a monad, a monoid? Yes, that can sort of fall out of API design where like maybe you're classifying after the fact, but I don't like having those two be conflated. I think it's better if it's just like there's just the API design. That's the one job you have when you're deciding what is the public and private split and what are the operations and how are they supported. Okay, so to sum up all this stuff, and then we can wrap up and look at some code if you want, because I took way more time to get through this than I thought I would. Um, Static dispatch, which is this is the new way to rock, is static dispatch. This is like really transforming the language in terms of like how the code looks, how simple it is to do powerful things in the language, um, structural ad hoc polymorphism, more concise code in terms of like you just don't need to fully qualify things as much. You can do this like method style syntax. Um, it's easier to learn, especially if you're coming from like an imperative or object oriented background, because pretty much all those languages have method style syntax. Like even Rust and Go and Zig, which are not object oriented, they all have method syntax. It's familiar to a lot more people. So the language you can focus more on the concepts and less on the syntax. Um, and yeah, it just looks familiar to more people. When I'm explaining the language, I can now focus more on the benefits and like the cool stuff about like the immutability, the pure functions, and all that, and not have to be like, okay, well, first let me explain to you how the syntax works and how currying works and all that. Just like, no, no, just look at this. It looks like JavaScript code, except it's way more awesome semantically. Um, so yeah, this is kind of a little like grab bag of all these things. If you want, we can I don't know. Look, like I can like breeze through some code very quickly. If you want to look at it, or we're kind of like over on time. I don't know what we're looking at in terms of like hard stop versus not. But yeah, thanks for sticking with me with all that. Happy to answer questions and also happy to go through some code examples if people are interested.
I want to see code, but I also wanted to ask, what version are you writing in? Is this like bleeding edge? Like, is this
This is so
what's
bleeding edge that I'm literally telling my editor to highlight it as Ruby because this like none of this will like compile
okay?
well, not none of it, but like I'm assuming if I run this, like the compiler will just be like to do, implement something.
hmm And it's
Um,
not, and it's not what's running. It's not like what's in documented on the rock language
right. Yeah, we
documented.
we
Okay, because
definitely
it's
have
static
not.
distinction. Okay.
Right. The docs are all about the like Rust version of the compiler, which all actually
Mhm.
works. So it has
Yeah.
that going for it. Like the stuff that's documented on the website, you can actually use that for real. This is all like, the plan is that in 2026 we will release version 0.1 of Rock,
Okay.
which will have all of this.
Nice.
But it's if we shipped it right now, it'd have to be version 0.0 because you can't, like do interesting stuff with it yet. We're surprisingly close to the milestone of you can do interesting programs in Rock, and the next milestone is like, hey, you can actually do like real stuff. Like there's actually a guy in Sweden who like all he does is write Rock code and he makes money doing consulting doing that. So like shout out to Nicholas on Rock Zula. But so he's obviously using the Rust compiler because that's like a real compiler. This is a very, very incomplete compiler. It's not production ready. But yes, all of this that we're looking at here is going to be the new stuff that that I just talked about, static dispatch and all that. Um,
So,
so-
so, so let me interject real quickly. So what I'd like to do is open it up for questions for a little bit,
cool.
and then a number of people said in the chat that they're happy to stay on for sort of as long as we'll go,
Cool.
and as long as Richard can go,
Yep.
and
Hey,
then
kids
what
down
we
for the night. I'm good to go.
so and awesome and so what we usually do is we would do like Q&A for a little while on the recording, and then usually we turn off the recording and keep going as long as we can go.
Yeah, I
So
mean, we can keep the
but
recording going if you want, just so we can have the code in the recording. But then we can also stop and just kind of hang out and chill and
yeah,
chat after that.
but so I wanted to open up for questions first, and
Cool.
see what questions there
Yeah, I can
are right
also
now.
go back to
I'll,
these. People want to see the slides or the code or whatever.
I'll just kick it off. Is With the new compiler, is the language server being developed in parallel, or would we have to wait for that even further?
Uh, I'm not sure how to answer that. We haven't nobody has started on a language server in the new compiler. Um, what I want to do, like the way that I want things to end up being, is that we have a sort of pluggable thing that you can use for the language server. So we have in the current compiler, the Rust-based one, we have this thing called Rock Glue, which basically is it's used for if you're doing like low level interop with another language. I managed to get through an entire Rock talk without talking about platforms and applications, which I'm very proud of myself for. But usually I end up going on a deep rabbit hole explaining all that, which I intentionally did not do for this presentation because, well, as it turns out, it was way longer than I thought, even without getting to that. But basically, what it will do is it'll just be like, give me a Rock program and I will call that rock, like the compiler will compile your program, and it will call that rock script that you gave it, passing in a like data structure that describes like the structure of your program's like external boundary, like all the types and all that, so that you can then generate, C bindings or Rust bindings or Zig bindings to your specific, rock code. Uh, I want to sort of do a version of that that's designed to be targeted at like editor extensions. So the idea is that one very obvious thing you could do with this is to do a language server, but you can also do things like code mod tools where it's like I want to be able to just like go over your code base and like, do like a code transformation or something like that because you have full access to all that stuff just in arbitrary rock code. Um, you could also write a linting tool with that, would be like another use case for that. Um, so that's what I want to end up with. Probably as an intermediate step, we will just to like do a little bit of like a corner cut and just have some sort of like temporary like Rock has like a language server, I don't know, Rock language dash server or something like that command that'll just like start up a language server that we've kind of hard coded. Ultimately, I don't want the language server to be in the compiler. I want that to be decoupled for various reasons. But yeah, until we have that more flexible, like you can implement the language server as a Rock thing on top of this sort of like compiler gives you static access to the information and in a way that a language server would have everything that it needed. Um, we'll probably just have some sort of like stopgap, like, okay, people want language servers while we're building the language. So here's a temporary thing that we'll take away later and replace with this fancier thing later, if that makes sense.
Wonderful. Thank you.
Cool. Other questions?
I have one, yeah.
Yeah.
Programming language design is really hard. There's so many ways of doing it, so many trade-offs.
I
Some
disagree.
languages
No.
some languages have like sort of a single designer or maybe like a benevolent dictator. Others are more designed by committee, others are complete anarchism and just try whatever. We'll see how it works out. I was curious where sort of on that scale is Rock, and do you ever sort of have conflicts within the development community about the direction of the language design, and how do you resolve those?
Yeah, so we have a rocklang.org/BDFN that explains this. So I came up with this term BDFN, which is benevolent dictator for now. Um, basically, like the TLDR is sort of like uh, we all talk about everything. There's almost nothing that will just be like unless it's something that I think is like small and uncontroversial, where I'll just be like, we're doing it this way. In which case people are like, yeah, obviously we're doing it that way. I'm like, yeah, I know. uh, but generally speaking, we talk about everything, and then like if like we try to come to a consensus, we being like people currently it's just like people in Rock Zulip. There's no like core team, like formal elected officials or whatever. It's just like we all just talk on Zulip because the community is small enough that we can just do that. Um, really, the benevolent dictator role is just like if we can't come to a conclusion, then like I have the final say. Also, I did like have a first pass design of the language, which it was a lot different from where we ended up today. Um, back in 2018 was when I started designing it. So of course, there's a very heavy bias towards just like the people who came to the language to participate in the first place were interested in the design that I originally came up with. And although the design has evolved a lot because of community contributions, like I did not come up with the idea from static dispatch for static dispatch out of nowhere. It was a couple of different people actually mentioned ideas in this vein, and then I kind of came up with like a concrete design proposal, which went through multiple iterations based on community feedback and stuff. So I would say in practice, the way it works is it's highly collaborative, like how the language gets designed, but there is like me at the end of the pipe saying like, nope, we're going this way. If we can't agree, then like, I'll make the final decision on like where we go. But honestly, most of the time we end up with like, if not full agreement, then it's sort of like, okay, um it's kind of clear like what the prevailing idea is and like maybe what direction makes the most sense, and it's almost never like I'm the only one who wants to go in this direction. It's generally speaking we do tend to go in the direction that like if you were reading the chats you could probably guess just from like the tenor of the discussion what was going to end up being the way that we would go, if that makes sense.
I got you. Thank you.
Cool.
So I have a question that I don't know. I feel like it sort of follows up on Florian's question in a way. So, um, you've been presenting, I think, at this group since maybe since 2020.
Was it?
Um, I think that's right.
Yeah.
And so like if I recall correctly, like the first time you presented, it was sort of like on Elm, and then you were like, oh, and by the way, I've been like working on this other language.
Yeah.
Um, I don't even know if it was called Rock back then. Maybe it
It
was.
was back then, yeah,
It
in
was
2020
okay.
for sure. Yeah.
Um, so anyway, and then you like we kept bringing you back because we really like you. And it's evolved a ton
For sure.
over the years. And so you talked about like releasing like, point one next year. And I'm kind of curious, you had mentioned sort of like all programming languages are experiments, and uh, seeing how much the language has evolved over the past 5 years, I'm kind of wondering, do you see the language stabilizing? Do you see it continually evolving? Or what parts stabilize? What parts
Yeah.
evolve? Where does the creativity continue?
Yeah. Okay.
Yeah,
I
you know
can
my
answer
question.
all those. So let's start with like which parts are stable and which parts are less stable. So, believe it or not, the standard library for Rock, I think the only way that it's changed since 2018 is like some of the names are different. Like I don't know if any of the types. I mean, obviously the static dispatch stuff means that like um the type of like equals will be different than it was back then. But that's about it. Like everything still like has the same sort of shapes, if that makes sense. With one possible exception of ad hoc polymorphism, because we've changed our ad hoc polymorphism system. Um, all of that really comes from Elm and like Elm's, in my opinion, like just world-class API design that Evan did. Not just for the standard library, but for Elm's like other supporting libraries, like HTTP and HTML and JSON, like all that stuff. Evan just did a really, really great job, I think, and really nailed it when it comes to um, like pure functional programming, really, really nice, simple APIs that are powerful and fast and like just just really lovely stuff. Um, all of that I think you still see, and like all of the things that have changed in Rock, none of that has really changed, in my opinion, like meaningfully. We just chose some new names for things. That's like the most significant change. Um, so that sort of core is still there. The way that I/O works, initially we use the same thing that Elm did, which is task basically for, which is kind of like Haskell's I/O, but combined with results. So you have like an error type built in. Um, we kept that for a long time, and then now we've moved that to the purity inference and like effectual versus pure functions, um, which is a certainly a bigger change than just a rename. But at the end of the day, like again, the programs really are not structured significantly differently. The code looks different because now you're able to just call like dot spawn, right, or whatever, in the middle of your code, or like make dir and write whatever. You don't need to do the same sort of like, I don't know, I don't want to say gymnastics, but like you don't need to do as much work, I guess, to make effects happen in Rock as you used to. But the effects are still happening in all the same places as they would have before, if that makes sense. That part hasn't changed. The platforms in that.
Well, I mean, the
Okay.
purity inference stuff seems pretty revolutionary. I mean, that seems pretty amazing to me. I haven't
How can I argue with that?
I mean, I mean, I don't. I, yeah, I don't know
Well,
how to.
so I think, I mean, to me, the cool part about it is to the degree that it's revolutionary, I would say that the way that it's revolutionary is that it preserves the really nice semantics of having a type level distinction between effects versus pure functions that have no effects. while revolutionizing the ergonomics of that because Haskell's do notation, um, like it's certainly a lot better than chaining the functions together by hand. But like in Haskell, if you're like, if I want to do like if file dot exists, right, like file name, then like you just cannot do that in Haskell. That's like that is impossible to write. You have to do like do, and then you have to call the file this and like give it a name and like whatever my bool, and then you can do the if like it's this whole ceremony thing, whereas it's like you can do this sort of thing in like any language that's not doing that sort of monadic style of I/O. To be fair, though, again, if you have algebraic effects, you get that, or sorry, you potentially get that same kind of thing. So in OCaml, you can do unrestricted side effects anyway, so you don't have it as a guarantee. But I'm pretty sure in Unison, the only way you can do effects is using algebraic effects. They don't support side effects any other way. So I think in Unison, you can tell in the type, and I think also in Coca, um, whether or not it's doing effects just based on which algebraic effects are in the type. Uh, but I think when I say it's like a revolution in ergonomics, it's like the learning curve again on like, is the type a um, you know, this type is I'm doing an effect. Uh, if it were a thin arrow, then it would be the type is I'm not doing effect. Right? This particular example didn't have any of those, but we saw plenty of them in the slides. Uh, that's great. I love that. It's super simple to explain. It's super easy to sort of get that first class reliable split in your code base of which ones are the pure functions, which ones are not. I really like the exclamation point. That's turned out really well, I think, to just be like, oh, where are the side effects in here? Okay, well, none of these are side effects. Oh, wait, there's one, right? It's just so easy to spot them. Like they just jump out the exclamation points. Um, but yeah, none of that is stuff that you can't semantically like you still get that split in Elm and Haskell, but you don't get the same ergonomic experience. So yeah, on the one hand, I can totally see why you'd use the word revolutionary, but in some ways it isn't. In some ways it isn't. In some ways, it's the same old rock as it was back in 2018. It just looks nicer in the like implementation side. So I guess what I'm trying to say is like the theme here is that the the shape of rock code has really not changed since the original design. Like very in very very minor ways. It's like instead of task you have thick arrow result or thick arrow try. Instead of like we renamed various things. Um, but like yeah, the distinction of like which things are pure, which things are effectful, that's been there from the beginning. It looks different now, but it's the same split. The programs are organized the same way. The APIs are the same way. You still have the same. There's no classes, there's no objects, there's no mutation. Mutation's always been behind the scenes optimization. All that stuff has been stable and feels very stable. Um, if I were to take 2018 rock syntax and write this, it would look wildly different. Like the body of this function. uh, so there have been a lot of syntactic changes and also a lot of changes in the way that, especially ad hoc polymorphism has worked, which leads us to all of the things that we're talking about now. We didn't have this question mark operator, which is just directly ripped off of Rust. It works exactly the same way it does in Rust. It's a way of doing early returns. We didn't initially have a concept of early returns or for loops or variables that you could reassign, and now we have all of those. Um, but yeah, so those parts of the language, I guess, have been less stable. Like ad hoc polymorphism, certainly the like imperative features are new, um, and the platforms and application stuff has been very stable. But ultimately, I mean, I do feel kind of bad that like Nicholas has a lot of breaking changes to deal with, and one of the reasons that we, in fact, the overwhelmingly main reason that we don't have a version number yet is just that one of my learnings from Elm was that Elm did this big breaking change in version 0.17, which removed this like foundational primitive of signals in favor of the Elm architecture, which was, in my opinion, in the opinion of 95% of the community, let's say, a very, very positive change that really unlocked like taking the language to the next level. And it was really, really great that that happened. But there were a lot of people who were very upset about that change. It was a small minority, But some people like quit the language because of it. Some people were very angry and very vocally angry on the internet about, understandably being like, hey, I thought this language was thing A, and now this language is thing B, and this is not what I signed up for, and now I'm just left out in the cold. Um, I'm very unhappy about this. Again, totally understandable. So I really wanted to avoid that from happening, and the best way I could think of to do that, while knowing that we're going to need to be experimenting before the sort of design that makes sense for this language emerges, um, is to just really, really strongly communicate like this is not stable. And the strongest way I could think of to communicate with that is like literally we only have nightly builds. There's no version number. That's how alpha we're talking here. Um, so once 0.1.0 does come out, there's still going to be an 0.2.0. It's not like we're not going to make breaking changes, but I don't think we're going to make breaking changes of this magnitude, or at least I don't anticipate any. I'm not saying we would completely rule it out, but it's more like we've already seen so many things be stable since the initial, design and implementation of the language, that these last things, it's really hard to imagine us changing like how ad hoc polymorphism works away from this because this really kind of addresses all of the pain points that I could identify from the previous way we were doing that. It feels like this all feels very cohesive. I can imagine us making breaking changes, but I think they're going to be much more minor and not in the like rewrite your code base kind of a level of change that like this type of stuff would be if you had a big rock code base in the old one. Which, again, apologies to Nicholas, but he's been a really really good sport about the breaking changes we've had over the years, of which this is just one of a series of things as we were sort of iterating on it and finding this design. But yeah, to answer your original question, like how stable is the language? I mean I can't give a comprehensive answer, but I would be pretty surprised if we ended up making any significant departures, any like major departures from what we're seeing here. I think this is what's going to be Rock 0.1.0. We're going to have some things that are technically breaking changes, and I want to be serious about following semantic versioning, where it's like, if your code might not compile, we'll bump the, I guess for O dot whatever, it's like, the one after the first digit. Um, and then eventually we'll have a 1.0. 1.0 I want to treat with a much higher bar than 0.1. 0.1 to me is just like we're kind of moving out of the like, experimentation, no guarantees, like, expect anything and everything to be, change overnight, without a ton of warning, to being like, okay, this is now a more like normal beta product. We're going to try to not break your stuff. There's probably not going to be major changes. There will be some breaking changes. So if you don't have any tolerance for breaking changes, you probably want to wait. But yeah, like expect a lot more stability than there has been in the past. 1.0 is a much stronger thing in my mind, especially because you have languages like Go and Clojure and I think Gleam is actually, I don't know if Gleam is in that category, but like certainly Rust also, where they're just like, yeah, like 2.0 is just like not planned ever. Like maybe we'll do one, but it's like really hard to imagine. Where instead we're gonna be on like version 1.200 or something like that, because just keep making minor releases and patch releases and that's it. Um, I think people by and large either expect that or expect that if there is going to be a version 2, it's going to be easy to migrate to because people talk about, Python 2 to 3 or Scala 2 to 3 and like it's like, yeah, we really don't want to be doing stuff like that. Or like Perl 5 to 6 where they just like rename the language to Raku, right? Um, at this point it's sort of like, okay, if we are calling the language 1.0, we're probably going to have to assume that if we ever want to make any kind of a change that could be considered breaking in the future, we probably need to do the like Rust editions thing, which is basically saying, um, you can opt into the new like syntax or whatever like breaking semantic change we've made, uh, but our all future versions of the compiler will support all the old ones too, and that includes like from a dependencies perspective. So you're under no obligation to upgrade. We will continue supporting the old way and the new way indefinitely in the same compiler every single time we do that, so that we're always technically on 1.0 and you can always just, opt in. I don't know if we want to go that far with it, but the point is that if we're talking about a 1.0, those are the types of things that I'm thinking about. So 0.1.0, the goal is 2026, sometime in 2026. I don't know exactly when. Um, 1.0, definitely not in 2026. I don't know when, but definitely not in that time frame. So
Hey,
that was kind of a
Richard,
long-winded answer, but hopefully it clears it up.
I've got some thoughts on the topic.
Sure.
Um, uh, my perspective as someone who's been following along with the development for a couple of years, I feel like it's both revolutionary and evolutionary at the same time. So the core of the language, the design is based on, I think, some really rock solid principles and inherited from, the likes of Elm, etc. And I think the process of discovery, it's been very non-linear, but it's been simplifying and cutting things away and reducing that core to the minimal set of, I guess, looking at simplicity. How do we deliver something that's very capable, but also very simple? And so I would say that's evolutionary. Um, Sorry, yeah. So that's my thoughts are that the core of the language is become simpler over time, the semantics. Um, on the other hand, there's the syntax, which looks very revolutionary from where we started. And
Yeah,
I think that's fair to say that it's revolutionary. And from the end user perspective, I think it will be a totally different experience to a lot of other languages. But the process of the journey has been evolutionary. It's been a discovery. Every single decision point has been informed by real experience, and I think that makes a big difference in terms of the confidence in why those decisions were made at every point. And I think it's why you see such a cohesive design in the syntax today. And so, based on all that, I have a lot of confidence that this is quite mature and polished, and I'm really excited to use it for Advent of Code. And I'm sure there'll be some minor tweaks, with the header syntax or there might be some things that change, but I think the core of the syntax and the semantics is really mature now.
I agree. Yeah, other questions?
Yeah, this is something I've seen discussed and I've never seen implemented. A syntax for, I guess it would be syntactic sugar for a recursive lambda expression where you have a function that isn't named, but it can call itself,
Hmm.
rather than like fully defining a Y Combinator in code. Thoughts on that?
Clojure has that.
Oh yeah?
Yeah, it's called the keyword is recur, and
Hmm.
does what you'd expect.
Would you ever consider implementing something like that?
I think I would have until we decided to add for loops. And I think it's kind of redundant with that. At that point, it's a bit of a I don't want to say party trick, but it's sort of like it's just like this is neat, right? It's not like
Yeah, I
this is
I will
practical.
admit I thought of
Um,
this question before you announced for loops.
yeah,
So
yeah. Um, yeah, I mean, there's a lot of things where we used to have. This is something actually, Luke. I don't know if you would have had to be watching the PRs because I forgot to mention this on Zulip, but like, uh, there was this debate that we had early on where I was like, I care a lot about the beginner experience. I know that one of the other things that is a lot trickier in getting into purely functional languages that like don't have a for loop or at least like a for each where you can like mutate stuff outside the lambda and that you give to the for each um, is just that like for loops can be used for so many different things that once a beginner learns how to do a for loop, it just unlocks this whole world of things you can do. Whereas in a functional language, technically recursion is that. It unlocks this whole world, but the problem is that the learning curve on for loops versus the learning curve on recursions is just like night and day. Recursion is like infamously something that beginners struggle with, and for loops is something that, unless you're dealing with like C syntax for them, like nobody struggles with. Like for A and B is like super easy for everybody to understand. Um, so uh, I was like, well, okay, well maybe we can like, and of course like reduce or fold or whatever is also like hard for people to learn. The way that we deal with that currently, which I'm not saying is like, the necessarily the best way to deal with this, is just like we have, I chose the name walk for these. So we have like walk and it's like, give me a list of things and a state and blah blah blah. This is the current like real docs. Sorry, it's not the updated syntax of what we're gonna have. And hey, it's the old pipe operator, right? Um, that will all be different when we revise all this. Uh, but then, of course, you end up with like, well, okay, so there's like walk, and then there's like sometimes you want like a little index in there. So there's like walk with index, and it's like, oh, well, sometimes you want, um, like other versions of that. So you want like, walk bang for like the version that can do like effects inside of that. There's like walk try, where it's like each one can like potentially return. Again, this is called result before we decided to rename that to try. Um, like there's all these different variations on this, and it's like, or you could just have four, and then you just like don't need a million different variations of this to try to be, beginner friendly. Um, and one of the nice things about having four is that it means we don't need to try to choose this, more beginner friendly name of walk. And the reason I wanted to go with that name is just like both fold and reduce have a problem of like not really suggesting that you're like walking over a list of elements in a list. And part of the reason for that is like, well, it doesn't have to be a list, it doesn't have to be a collection. It could be like, an option or a maybe or a result or whatever. Those can all have folds too. It's like, okay, yes, technically, but like, is that actually useful? Or I understand why for historical reasons it would, have a different name, but I wanted to try to be beginner friendly. Now that we have four for beginners and also for, the occasional advanced user use case as well, it's like, yeah, we can just go back to calling this fold because that way, if you're coming from a functional background, you're very comfortable with that function. I don't need to like explain it to you. You're just like, that's what I'm going to reach for anyway. And you're probably going to expect it to be called fold because you're coming from a functional background. So it's kind of like the best of both worlds. If you're coming from a Haskell or an OCaml or something, you're not looking for walk inside of here. This is actually something we debated is like, how do we solve that problem of like somebody's looking for how do I find, like I type in the search box, I type fold and it's like no results. What? Well, how does this functional language not have fold? Oh, well, if you look for walk, then like there it is. But so this means that like we can just go back to calling it fold. Beginners coming from an imperative background are not going to reach for that anyway, so they don't care what like it doesn't matter anymore what the name like how self-explanatory the name is because they can just use for. Anyway, putting all that together, I don't think we need to have a recursion like a self-recur thing or anything like that for anonymous lambdas because yeah, like you don't need to use recursion as much when you have four.
Yeah, that makes a lot of sense. And actually, one of my like kind of complaints of trying to learn it was the fact that the standard library you kind of need to use to avoid the boilerplate, but it is different than other standard libraries, so
Yep.
it's a little bit difficult to get started.
Yeah, there are some things where it is going to be like still some things are different. So like a classic example of this would be like filter. Like we don't call it filter, we call it keep if and drop if. Um, right? I, that is one where I do think beginners like mess that up a lot. Like they say, you know, uh,
I actually very much agree with filter is kind of ambiguous.
yeah. But if you're used to it, right, you're gonna search like, okay, where's filter? On the other hand, it's like, well, if you're coming from an FP background, like like what filter is, and so that is one of those cases where we have. Oh, I should check if that's in the list. We have a list of like common synonyms in the new compiler where it's basically like if you get an error that's like a naming error, like if you type in dot filter and it doesn't exist, we actually have a mapping of like, oh, did you mean keep if? Because that's what we call it in this language. It's just like a mapping of like common, you might be expecting it to be called A, but here we call it B. And similar like stuff like if you write like lowercase true, which is how it is in a lot of languages, we do uppercase true because it's a tag union. Um, if you do lowercase true, we can be like, oh, it's capitalized here, and part of that, fast friendly functional friendly error messages and all that. But yeah, there is some tension there when it comes to keep if and filter that at least within the case of fold we can get rid of. Other questions? Cool. Well, so I can keep it super fast because we're way over on time. So apologies slash if you've been enjoying it, then like yay. But so I basically like made this little quick little example of like here's how like a rock script would compare to a Python script because this is like kind of one of the Actually, let me side by side these. Um, so I probably have to zoom out more than is desirable to fit them both. But basically, it's like, okay, so you have your imports at the top. Because we use pound as our comment syntax, you can just use the like hash bang thing at the top for like these will both just work. So you can just like mark your rock scripts as executable, and that'll just work. Uh, we do have a little bit more up top in the way of like imports because we're specifying these dependencies. This is a cool thing I think that has been true about Rock for years, is that without getting into a huge tangent on how we do our dependency management, I think it's novel and really cool. And basically, you specify URL. Part of the URL has to be a hash of the contents of the tarball you're downloading, which means that if the URL gets like compromised or like tries to make a change to this, the worst case scenario is you just get an error at compile time that says like, "Hey, this didn't match its signature." Um, we download this into a local cache folder that's in your home directory. So you can have dependencies in your script. They will automatically get installed. There is no like rock install. You just say like I said, just like rock my script.rock. That's it. Nothing else to say. And it will just download these dependencies and cache them. Since these are immutable and the immutability is enforced by this hash in the URL, that means that you don't have to worry about like, oh, do we need to go look for an update? It's like, no, there are no updates. It's immutable. We could just cache it and then we never have to download it ever again. Uh, there's also a concept, we don't have this implemented in the new compiler yet, but of like semantic versioning within here. So if you have dependencies that have like transitive dependencies, we actually can go through and solve like just based on this, what is the lowest um, number that will satisfy all of your like minimum requirements. And we treat major versions as like different artifacts. Anyway, point is like just by specifying this one URL that has all the information about how to go get it, how to like security features, also like versions for like sharing things across multiple dependencies as long as the minor versions line up. Um, and that all happens automatically when you run it. So unlike in Python, like typically if you run this, it'll be like error. What is requests? I don't understand. And like, oh God, now I need to like go learn how to do like virtual environments in Python or like whatever. Um, None of that happens. It's just like it all just works. Like you just have .rock script. It also doesn't create like a node modules directory in your local folder. This is just downloaded into um, like your home directory or like XDG paths or whatever if you're on Linux. So that basically it's like a good script, it doesn't pollute the local directory. You just run the script and it just runs. But if you have dependencies, it just goes and grabs them for you. Um, so that's how you did imports. We have this like, run command thing like Python has, the doc string is like underneath the function. We put it above it, whatever, same basic thing. I mentioned this earlier, but like we do have the, just the one syntax for defining functions, which is like lambda. There's no separate like fn keyword or def or anything like that. It's just like, nope, just equals. That's it. That's how you define a function in Rock always. Um, and then basically, so then you have your arguments, and then here's the function body. Python has significant indentation. We used to have that, but we actually don't anymore. Our new syntax is completely white space insensitive. You can just put whatever white space you want. Okay, I shouldn't say completely insensitive in the sense that like if I put a space here, like now there's not a space before. Putting a space before the dot does do something different. Like you'll get an error if you do that. But basically, like we don't have semicolons, right? We have like just separating these things by white space at all is all you need really. Um, so yeah, then you have like process equals subprocess dot run. Like this would be a little bit of a different API where I think you would use like a process builder to do like, okay, like I'm gonna like specify the current working directory or this or that. Whereas in Python, you would have instead of like a builder, you would do this sort of optional arguments thing where you can like optional named arguments. This is one of the many things that we would just use static dispatch for. It's like, yeah, if you want to say like configure these things, you would just, do dot current working directory dot, check dot whatever, if you wanted to specify those. Um, and of course, spawn would have an exclamation point because that's the actual, effect. This question mark is just syntax sugar for basically like, I got back a try. If that try was an okay, then great. Unwrap it and like keep going. And if it was an error, then like early return with that error. So this is stolen directly from Rust. In Zig, this would be the try keyword in Zig, but we went with the question mark at the end. We have string interpolation. It looks like this, the pretty standard stuff. And then yeah, you can just basically be like, yeah, error command failed. I didn't talk about the like error handling in Rock, but it's really nice. These just kind of accumulate, and then you can just do a I guess I'm not doing it here. You can do like a exhaustive pattern match over all the different error types that you accumulate in your function, and that's all. That's not even a special separate language feature. It's just a way that our tag unions just naturally work because they're structural algebraic data types like OCaml's polymorphic variants. You're familiar with those, but they're a little bit different, but they're based on those. Anyway, yeah, so that's run command in Python and in Rock. And then here for like in Rock we call it main, but in Python you would just be like, it's the top level, just run stuff. We do actually have a separate like you do define a function named main. Um, yeah, so this is based. I ported the script based on part of our like how we build our website, like the rocklang.org. So part of that is like going in the latest nightly release because we actually do have a little REPL right here. So this is all WebAssembly. So like I can do like 1+1 or whatever. Um, uh, yeah. So basically, this is that. Like, go get that. I came up with this API. This doesn't exist at all, but I think it'll be really cool when it does exist. Is like sort of a streaming, like piping API. So you can say like, okay, I'm going to make an HTTP stream for a GET request. This is like no headers. And then I can like pipe it to like, okay, after I get the response back, I want to like decompress it. And then I want to pipe it to like a tar that's like, extract all of it from like, the root directory and then do like the, make dir and write on like every single like directory that we get in. And then like map error is just like transform the error if we get one, little lambda in here. Uh, for like, we're basically renaming this particular type of error to be like a download error as opposed to whatever the normal like HTTP error is. So we can kind of sort of tag that as a more specific error. And then finally we call run on the URL. So here's the Python equivalent of that. They're doing like try catch because that's how Python does error handling. Um, simplify oh yeah, then they do like, oh yeah, so this is all not like streaming in Python. I could have written it to be this non-streaming style, but I thought it'd be cooler to like demonstrate how this might work in like a streaming pipeline style. Okay, so then we have this part, the simplify the folder name. So in Python, you do this with like um, glob, whereas here I would do like, okay, do an ls to like list the directory structure and then a dot find. And then, this is just going to be a lambda that's going to traverse each of the directories in that entry, sorry, the directory entries in that came back from that ls operation and be like, okay, if it's a directory, does it start with rock nightly? That's what we're looking for. In Python, it's more of a like imperative, like os.rename type of thing, whereas I would actually, in rock, this is just how I would do it. I would do it with the only side effect being like the go get the directory, and then it would just feel like a pure function to filter it. And then finally, yeah, just be like execute rock version. That's that. Using the run command thing that we wrote earlier. And then, yeah, then like some more run commands. So I guess the main thing that I wanted to do with this was to demonstrate that like this is what Python is like really, really commonly used for and considered very good at is like writing a small script. The Python one is, yeah, they're almost exactly the same number of lines of code actually. But I can point out a lot of really nice properties that the Rock one has. Like this has full type safety. Every single thing in here is type checked. I didn't write a single type annotation on purpose because I just wanted to demonstrate that if I'm writing a script, I probably honestly would not bother to write. I might write a type annotation on this one, but like I certainly wouldn't bother on main or like I wouldn't type any of these variables. It's like yeah, just it's a script, just do the thing. Um, this HTTP stream thing is gonna like run faster. We have the like dependencies thing that's nicer. We have the error handling. If I did actually want to introduce some error handling into here, I think I would have a better experience than the like try catch thing, which is kind of defensive, whereas all of this is going to be exhaustive. So if I were choosing to handle the errors, I would just do like a pattern match on them and just be like, okay, here they all are. Every single thing, like the command failed, the download error, all of that would just show up. And if I forgot to handle one of them, then I would get an error. Now, as it happens, I'm intentionally choosing to ignore all of those. Um, but if I wanted to, I would. I don't need to do defensive try catch anywhere because all of my explicit points of like control flow changing are visible in the code with the question mark, which is syntax sugar for doing an early return. And I know that. I can see where all of the side effects are because of the exclamation points. Um, and yet, I would claim that if I were a Python programmer reading this, I could probably figure out what all this is doing. If I had some docs, to know what like, this pipe thing does. Um, but like none of this, even though this is like a functional programming language that is as hardcore as Haskell is, arguably more hardcore because we don't have unsafe perform IO, about isolating side effects and separating them from effects. But it's like as easy to read as Python and as concise for like scripting. Um, Except that, of course, if you want to write like a big, robust, code base out of this, you're gonna have a way better time doing that with Rock that I would claim than you would with Python. Um, so this is really, to me, kind of the payoff for all the stuff I just described. It's like we get all these amazing semantics, and yet we can compete, I think, quite powerfully with Python. Uh, we did do a little benchmark, by the way, of like when we first got Hello World working in the new compiler, and it was about as fast as Python to run Hello World, even though we're doing all the like type checking and we have the whole platforms and applications thing. Like our compiler is doing way more work than Python is to do the Hello World, but it's like about the same amount of time, which is also pretty cool.
When you
Um,
say the same amount of time, is that considering compilation and runtime, or is this
yeah,
Python just scripting it? Amazing.
Exactly. Yeah. So literally like you use like the time command and then like rock my script.rock and then time Python 3, Python script.py. And it was like I think the Python one was a little bit faster, but it was like barely. Actually, I think we used Hyperfine instead of time, actually, if I remember right. But anyway, yeah. Now that we've added more to the compiler, maybe that's not as true. I'm not sure, but I would actually guess it's probably still about the same. Um, but yeah, so I love this because to me, this is like a really great step in the right direction for like the ergonomics of getting into the language. It's like I can just show this code to a Python programmer. If they have never done any functional programming in their life, they can probably just understand what this is doing pretty much. Like the question mark might be honestly the most confusing thing, and then like that actually comes from Rust, not from a functional language. Um, it's just really straightforward, and yet the semantics I love. This like I can sort of feel, even though this doesn't look like Elm code at all. Um, I can feel the Elm influence in the APIs and the way that the code is separated, and like which functions are pure and which ones are effectful and all that. Um, and yeah, I'm just thrilled to actually be able to use this, and we're very very close to having the new compiler able to make it so that everyone can try this out. I did start to like do a little like web server one so you can kind of see what that looks like. But yeah, that was more just sort of like how would it look to get your like secrets out of environment variables and stuff like that, and like create a database pool and whatnot, and like do some logging things and whatnot. Yeah, but anyway, this would be like kind of how you like do your like pattern matching on your uh, routes and whatnot, or at least one way you could do that. So, um, yeah, I think that's a good place to stop. Any questions on yeah, absolutely any of that, or should we can stop the recording and just kind of chat? But either way, thanks for letting me run so far over. I appreciate it, and yeah,
Well, this is great. Thank you so much. So thank you. Yes, let's just stop the recording and then we can keep chatting. So
sounds good.
thank you so much. Really appreciate it.